Welcome to Quiet Universe, where we dive deep into the mysteries of our cosmos, unraveling the secrets that keep us all gazing up at the stars with wonder. Tonight, we're tackling one of the biggest questions of all, literally, the Big Bang. It's a theory that's been around for nearly a century, yet it still boggles the mind, raising more questions than answers. What really set the universe into motion? Was it a random event, or is there something far bigger happening, beyond our comprehension? And what about time? Did it all start with that one massive explosion? Or are we just part of an endless cycle of creation and destruction? Imagine this for a moment. All the matter, energy, and even the space around you compressed into a single point. A point so dense and so tiny that it's hard to wrap your head around it. Then suddenly, for reasons still unknown, everything explodes outward and the universe as we know it begins. The Big Bang wasn't just some explosion in space. It was the moment space itself began expanding, creating everything in its wake. Galaxies, stars, planets, even the time you're experiencing right now, all emerged from that single, chaotic instant. But what caused it? That's the burning question, isn't it? Scientists have some theories, but none have a neat answer. Maybe it was a quantum fluctuation, a random flicker in the void. Or perhaps the universe is just one small part of something much grander, a multiverse, where our Big Bang was just one in an infinite series of cosmic events. There's even the idea that our universe could have been born from the collapse of a previous one, the cycle continuing on forever, like a cosmic heartbeat. It's fascinating, and honestly, a bit overwhelming. And speaking of time, did it even exist before the Big Bang? If the Big Bang marks the beginning of everything, does that mean time itself started ticking at that very moment? It's a strange idea, but in a way, the Big Bang isn't just the birth of the universe. It's the birth of time as we understand it. Before that, we don't really know what before even means. Some physicists argue that time could be cyclical, part of an endless loop of universes expanding and contracting. Others suggest that time, as we experience it, may be a dimension that's tangled up with space itself, and that both came into being with that first bang. The more we think about it, the more we realize how much we don't know. And maybe that's what makes this theory so captivating. So as we venture through the universe tonight, we'll peel back the layers of the Big Bang Theory, exploring not just the science, but the philosophical and existential questions it raises. What does it mean for us to know the universe had a beginning? Does that change how we think about existence? Or are we just tiny specks in an ever-expanding cosmos? Stick around, because things are about to get cosmic. The question of what caused the Big Bang is one that has haunted humanity for generations. We find ourselves on this small planet, looking out into the vastness of the universe, wondering how it all began. The moment of the Big Bang feels like the ultimate mystery, a starting point for everything that exists. But the deeper we probe into it, the more elusive it becomes. Imagine being at the edge of a dark, infinite abyss, staring into a place where time itself begins, and realizing that our minds may never fully grasp what lies beyond that threshold. At the core of this enigma is the idea that the Big Bang wasn't just an explosion, but rather the sudden expansion of space itself. Before that moment, there wasn't an empty void. There was no space, no time, no before. The laws of physics, as we understand them, didn't exist. To try and picture what happened before this event is like trying to imagine a color you've never seen. It slips away the moment you try to define it. There is no clear cause that we can point to in the conventional sense because causality, as we know it, may not have existed before time began. Some scientists suggest that the universe may have originated from a singularity, a point where density becomes infinite and the known laws of physics break down. This singularity could have been born from the collapse of a previous universe or from fluctuations in a quantum field. But even these ideas feel like echoes in a chamber where answers vanish as quickly as they appear. The notion of a quantum fluctuation, a random blip in a vacuum that suddenly sparked all of reality, leaves us with more questions than answers. What gave rise to that fluctuation? What conditions led to that moment? In many ways, it feels like we are chasing shadows, trying to solve a puzzle where pieces keep disappearing. For a person, there's something deeply unsettling in thinking that everything we see, touch, and know might have been born out of a random event or an unexplained fluctuation. We crave stories with beginnings, middles, and endings, stories that make sense. But the origin of the universe may not offer such comfort. It could be that the cause of the Big Bang lies in the nature of existence itself, beyond the scope of our current understanding. Some believe that we may need new theories, ideas that go beyond what we know about quantum mechanics or general relativity, to even begin to approach the true cause of that moment. Yet, there's also something profoundly beautiful about this. The very fact that we, tiny beings on a planet spinning around one star in a galaxy among billions, are capable of asking these questions feels like a testament to the wonders of the universe. We are the product of that ancient explosion, fragments of stars born from that initial spark, pondering the same event that gave birth to us. In that sense, the cause of the Big Bang isn't just an abstract, cold fact waiting to be discovered. It's deeply personal, intertwined with our own existence. We don't know for sure what caused the Big Bang, and perhaps we never will. But in our search for answers, in every new theory and observation, we are connecting ourselves to that mysterious beginning, to the very fabric of space and time that birthed us. And even though the cause of it all might remain hidden, the fact that we can even ask such questions speaks to something truly extraordinary about us and the universe we inhabit. The idea of what existed before the Big Bang is one that takes us to the edge of what we can even imagine. We live in a universe shaped by time, and it's hard to let go of the notion that every event must have something before it. Yet, when we talk about the Big Bang, we are not just talking about an explosion that set things in motion. We're talking about the birth of time itself. It's a concept that seems to defy everything we experience in our everyday lives. What does it mean for there to be no before? It feels unnatural, unsettling even, because our minds are wired to think in terms of cause and effect, of past and future. Some theories propose that perhaps there was something before the Big Bang, but what that something was remains unclear. One idea is that our universe could be part of a larger multiverse, where countless other universes exist with their own unique rules of physics. In that case, the Big Bang might have been a local event within a grander cosmic framework. This would suggest that before our universe, another existed, either coexisting or preceding it. But even this multiverse idea leaves us with endless questions. If there was a universe before ours, what was its fate? Did it collapse, or did it expand forever, leaving behind nothing but the seeds of what became our cosmos? And why did the cycle of universes begin in the first place? The answers seem as unreachable as the stars themselves. Then there's the theory of a cyclical universe, where everything repeats in a constant loop. In this view, our universe could be one of many, endlessly expanding and contracting. What came before the Big Bang might have been the collapse of a previous universe, a final breath that gave way to the creation of ours. It's an idea that appeals to our desire for continuity, for some kind of eternal rhythm that we can make sense of. But even here, the question lingers: what was the very first cycle, the moment when everything began? If time is cyclical, when did the wheel start spinning? There's also the possibility that before the Big Bang, there was nothing. Not the kind of empty space we think of, but a true absence of everything. No space, no time, no existence at all. The concept is almost too abstract to grasp. It's hard to imagine nothingness in a universe where everything we know is made up of something. But if time began with the Big Bang, then the idea of a before becomes meaningless. It's as if trying to ask what's north of the North Pole. The question itself starts to fall apart. This idea forces us to confront the limitations of our understanding, to accept that some things might simply be beyond the scope of human thought. Yet, for all the mystery that surrounds what came before, we can't help but keep searching for answers. There's a deeply human quality in our need to explore the unknown, to fill the gaps in our knowledge. Even when we come up against the edges of what we can comprehend, we push forward, driven by the sense that somehow, somewhere, an answer exists. Whether there was something before the Big Bang or not, the mere act of asking the question connects us to the vastness of the universe and the wonder of existence itself. So, what was there before the Big Bang? Maybe there was a universe before ours, part of a cosmic cycle that stretches endlessly backward. Maybe we are part of a multiverse, where different versions of reality exist beyond our reach. Or maybe there was nothing at all, an incomprehensible void waiting for time to be born. The truth remains just out of reach, but the beauty lies in our quest to understand. We are, after all, children of that distant moment, still seeking to understand our origins, still wondering what lies beyond the horizons of space and time. There's something almost haunting about the idea that the Big Bang, the beginning of everything we know, might have been triggered by something external, something beyond the borders of our universe. It invites us to think of the universe not as a singular, isolated event, but as part of a much larger, more complex story. It's a concept that takes us out of the familiar and into the unknown, suggesting that the universe itself might be just one chapter in a broader cosmic narrative. If the Big Bang was set in motion by something else, perhaps a collapse of a previous universe or an interaction with another universe, it forces us to confront the idea that our reality is not the only one. The possibility that the Big Bang could have been caused by the collapse of a previous universe suggests a kind of continuity, a chain of existence stretching back before time as we know it. In this scenario, the universe before ours might have expanded for billions of years before eventually running out of energy, collapsing inward in a process called the Big Crunch. At the very end of that universe's life, the intense gravitational forces might have compressed everything into a singular point, triggering a new Big Bang and giving birth to the universe we now live in. The notion of a cyclical universe has a certain appeal, offering a comforting sense of eternal renewal. One universe dying, another being born from its ashes. It speaks to the human need to find patterns in the chaos, to believe that even the most incomprehensible forces are part of some larger order. But if the Big Bang was triggered by the collapse of another universe, it still doesn't answer the question of where it all began. What caused that first universe to exist? What set the cycle in motion? The deeper you dive into the question, the more it feels like trying to follow a thread that keeps unraveling, leading you further and further away from any solid ground. And yet, there's something undeniably fascinating about it. The idea that our universe is part of a vast, interconnected web of realities, each one affecting the next in ways we can barely comprehend. Another possibility is that the Big Bang was triggered by the interaction with a different universe entirely. In theories like the multiverse, our universe might be just one bubble among countless others floating in a higher dimensional space. Perhaps two of these universes collided, their energy and matter fusing together in a violent burst that set the Big Bang in motion. It's a mind-bending thought that somewhere out there, beyond the limits of our universe, other universes could exist, each with their own rules, their own physics. Some might be similar to ours, others radically different, perhaps even unrecognizable. The collision of these universes could have been the spark that ignited our reality, a cosmic event that gave birth to everything we see and know. There's something deeply unsettling about the idea that the birth of our universe might have been the result of something so random, so external. We want to believe that the universe is a self-contained story, something that makes sense within its own boundaries. The thought that it could have been triggered by something outside of itself, something we might never understand, makes us feel small, vulnerable even. But at the same time, it speaks to the vastness of existence, to the idea that there's so much more out there than we can ever imagine. Whether the Big Bang was caused by the collapse of a previous universe or the collision with another one, it reminds us that the universe is far more mysterious and complex than we can ever fully grasp. We are drawn to the idea of origins, of understanding where everything comes from, but the more we seek answers, the more we realize just how little we know. The external forces that might have triggered the Big Bang lie beyond our reach, at least for now. But that doesn't stop us from wondering, from pushing the boundaries of what we know, always searching for a glimpse of the greater forces that shaped our universe. There's a kind of beauty in that uncertainty, in knowing that we are part of something much larger, something far older than the universe itself. The idea that the Big Bang marks the beginning of time is a concept that feels strange and almost alien to us. We live in a world where time is so deeply ingrained in everything we do. Every day is structured by the passing of hours, every memory is tied to a moment in time, and every action we take feels like part of an ongoing flow. But when we look at the Big Bang, we're confronted with the possibility that time itself might not have always existed. It's a difficult thought to wrap our minds around. After all, how could there be a time when there was no time? What makes this question so fascinating is how it challenges our understanding of the universe. If time began with the Big Bang, it means there was no before, in the traditional sense. It's almost like trying to imagine a story that starts without any pages before the first chapter. The Big Bang wouldn't just mark the birth of matter and energy, but the very fabric of time itself. And with that comes the realization that all the cause and effect, all the past and future that define our existence, are tied to that moment. The idea that there was no time before the Big Bang strips away any sense of what we think of as continuity, leaving us with an event that simply exists on its own, without any before or after until time itself begins to flow. But not everyone is convinced that time started with the Big Bang. Some theories suggest that time might have existed before, even if the universe as we know it didn't. One possibility is that the Big Bang was just one moment in a much larger, perhaps eternal, cosmic cycle. In this view, time stretches infinitely in both directions, with universes being born and collapsing over and over again. Each time, a new universe springs into existence, expanding and evolving just like ours, before eventually fading away and giving rise to the next. If this is true, then time didn't begin with the Big Bang. It merely carried on through the birth of our universe, just another chapter in an endless sequence of cosmic events. There are also theories that propose time as something even more mysterious, an emergent property of the universe, rather than something fundamental. In this view, time as we experience it only comes into being as the universe expands and evolves. What this means is that before the Big Bang, time might have existed in a different form, or it might not have existed in any way that makes sense to us. It's almost like trying to imagine what it would feel like to live in a place with no sense of direction. The rules that govern our reality wouldn't apply, and time as we understand it would be something entirely foreign. These possibilities leave us with more questions than answers. Did time truly begin with the Big Bang, or has it always been there, running quietly in the background of a much larger, grander cosmic stage? And if time existed before the Big Bang, what kind of universe, or universes, existed along with it? There's something deeply human in our need to understand time, to anchor ourselves in the past and look toward the future. We want to know where we came from, not just as individuals, but as part of a much larger story. Yet, the more we explore the nature of time, the more it slips through our fingers, revealing how little we truly know. Whether or not time existed before the Big Bang remains one of the great unanswered questions of science. But in some ways, the search for an answer is just as important as the answer itself. We are beings bound by time, living in a universe that was born out of a moment so far beyond our understanding, yet somehow still connected to us. And whether time has a beginning or has always been there, it shapes every part of who we are and everything we will become. The notion that the Big Bang could be part of a larger cyclical model brings with it a sense of endlessness, a rhythm that stretches beyond what we typically imagine when thinking about the universe's fate. It's an idea that offers a kind of cosmic rebirth, suggesting that our universe may not be a one-time event, but just one phase in an eternal cycle of expansions and contractions. Instead of picturing the universe as having a single, definitive beginning with the Big Bang, the cyclical model paints a picture of the universe as something that undergoes constant renewal. In this view, after expanding for billions of years, the universe would eventually slow down, reverse course, and begin contracting, only to collapse back into a singular point, which would trigger another Big Bang and start the whole process over again. It's a comforting thought in some ways, the idea that even the universe doesn't face an ultimate end, but instead continues to rise and fall like some vast cosmic breath. This cyclical model taps into something very human, a desire to see patterns in nature that are both predictable and reassuring. We are familiar with cycles in everyday life. The way seasons change, the way night becomes day, or how life leads to death and new beginnings. To think of the universe itself as part of a larger, eternal cycle satisfies that craving for order in the chaos. It gives us a way to imagine that even when everything seems destined to end, there's the promise of renewal somewhere down the line. The stars may one day burn out, galaxies may collapse, and the universe may fade into darkness. But if the cycle continues, it will all begin again, just as vibrant and full of life as before. Of course, while this model offers a kind of poetic symmetry, the reality is far more uncertain. The idea of a cyclical universe raises as many questions as it answers. What causes the universe to begin contracting after expanding for so long? And what happens at the moment of collapse? Does everything truly return to a singular point as it did before? Or does the cycle change in ways we don't yet understand? Could there be slight variations in each cycle, subtle shifts that make each universe a little different from the one that came before? These are the kinds of mysteries that haunt this theory, hinting at a deeper complexity to the universe than we may ever be able to fully grasp. One challenge to the cyclical model is the fact that, according to our current understanding, the universe isn't slowing down. In fact, it's speeding up, driven by a force we call dark energy, which seems to be pushing galaxies apart at an accelerating rate. If the universe is expanding faster and faster, it's hard to see how it could eventually reverse course and start collapsing again. This acceleration suggests that the universe could continue expanding forever, growing colder and emptier until nothing but distant remnants remain. Yet, this doesn't necessarily rule out the cyclical model entirely. It's possible that the force driving this expansion could change, or that our understanding of dark energy is incomplete. Maybe the universe will find a way to contract after all, in some far-flung future where the rules we think govern the cosmos begin to shift. There's also the question of how the cycles began in the first place. If the universe has been expanding and contracting for eternity, why? What started the cycle, if it had a start at all? Or is it possible that there is no beginning, no first Big Bang, but rather an infinite series of cosmic events that stretch back into the depths of time without end? The cyclical model offers a way to think about the universe as something eternal, but it also forces us to confront the limitations of our understanding. We're not just talking about one universe, one singular event, but an endless loop that challenges everything we know about beginnings and endings. What makes the cyclical universe theory so compelling is how it invites us to think about the cosmos in a different way, not as something that will one day end in some distant cataclysm, but as part of an eternal process. It's a humbling thought, reminding us that our universe, with all its stars and galaxies, might just be one in a long line of universes, each one rising and falling, creating and destroying, in an endless dance that we can barely begin to comprehend. And yet, even in its complexity, there's something beautiful in imagining that we are part of a much larger cycle, one that connects us to the vastness of the universe in ways we're only beginning to understand. The universe is expanding at a rate that is both mesmerizing and unsettling, as if space itself breathes with a silent, unstoppable rhythm. This expansion isn't just things moving apart like pieces drifting on a river. Space itself stretches between them. Imagine two dots on the surface of a balloon. As you inflate the balloon, the dots don't move on their own. The surface between them stretches, pulling them farther apart without either needing to budge. That's what's happening on the grandest scale imaginable. Galaxies are not flying away from each other in the traditional sense. They are being carried along with the expansion of the very fabric of space. The current speed of this expansion is described by something called the Hubble constant. The latest measurements suggest that for every million parsecs of distance, 1 parsec being just over 3 light years, the universe stretches by about 70 to 74 kilometers per second. This means that for every additional slice of space between 2 points, the separation accelerates. Galaxies that are farther apart from each other experience this stretching more intensely. If you look at a distant galaxy a billion light years away, it's moving away at thousands of kilometers per second, and the farther out you peer, the faster things seem to recede. Eventually, you reach a point where some galaxies are moving away so fast, not even light can bridge the ever-growing chasm between us. They vanish into the cosmic horizon, as if they were phantoms slipping out of reach forever. What makes this expansion even more mysterious is that it's not constant, it's speeding up. Think of it like tossing a ball into the air and watching it accelerate upwards instead of slowing down. This accelerating force is attributed to something scientists call dark energy, an invisible and still poorly understood presence that behaves like a subtle pressure across the cosmos. It's as if the universe, despite being born from the fiery collapse of everything into a single point, cannot help but drift apart in every direction, tugged by an unseen current that grows stronger with time. In human terms, the universe's expansion is like relationships that grow distant, not because of deliberate action, but because life pulls people in different directions. Even if no one means to drift away, time and space have a way of introducing gaps that can't always be bridged. The universe is littered with countless galaxies that once were much closer together, but now they exist in a kind of cosmic estrangement. Every moment, space stretches a little more, like a goodbye that becomes permanent, not with a bang, but with a slow, inevitable pull. It's humbling to think that the night sky, filled with light from distant stars and galaxies, offers a glimpse of things that are now far beyond our grasp. Light takes time to travel, and the things we see in the sky now are often echoes of objects that have long since faded from view, forever out of reach, victims of an expanding universe that refuses to stay still. This silent stretching won't stop, not even in billions of years. It's like watching the tide pull away with no shore in sight. the horizon slipping farther and farther until one day everything vanishes into the deep, quiet dark. The fate of the universe hangs on a delicate question. Will the expansion continue endlessly, or will it slow down, turn back on itself, and collapse? For the longest time, it seemed reasonable to believe that all things must come full circle. Just as an arrow shot upward eventually loses momentum and falls back to the earth, perhaps the universe, too, might reverse its course. After all, the Big Bang began with unimaginable force, scattering matter and energy in every direction. But gravity, the glue that binds everything together, never stopped pulling. Every star, galaxy, and black hole tugs faintly on every other piece of the cosmos, as if trying to coax the universe to reunite. There was a time when scientists thought that this gravitational pull might be strong enough to halt the expansion one day. If the universe were dense enough, if there were enough matter packed into it, the stretching would slow to a stop and reverse, pulling everything inward until the entire cosmos folded back into a point, an event they call the Big Crunch. In that vision, the universe is a cycle. Expansion followed by contraction, death followed by rebirth, like a cosmic heartbeat that pulses forever. But what we've discovered more recently complicates this picture. Instead of slowing down, the expansion is accelerating, driven by a strange, unseen force we call dark energy. It's as if the universe, having stretched a bit, now finds itself addicted to the idea of growing larger, accelerating into infinity with no sign of ever stopping. If dark energy continues to dominate, the future becomes unsettlingly lonely. Galaxies will drift apart so far that they fall out of sight, like old friends lost to time, unreachable no matter how far you travel or how loudly you call. In such a universe, expansion is not just inevitable, it's endless. In the distant future, even atoms may be pulled apart, leaving behind a cold, empty expanse where not even starlight remains. This scenario is called the Big Freeze, where time itself feels stretched thin, and the universe becomes a quiet, featureless void. There's still a flicker of uncertainty, though. We don't fully understand dark energy. What if it changes over time? What if it falters and gravity begins to take hold once more? It's like waiting to see if a pendulum will stop swinging, or if it will suddenly, unexpectedly reverse its arc. The future could hinge on forces we barely grasp. Perhaps one day, the universe will decide it has wandered too far and begin to draw everything back inward, collapsing in a final moment of reunion, a slow return to the singularity from which it all began. But even if that were to happen, we are talking about scales of time so vast they defy imagination. For now, all we know is that the universe is in motion, its path uncertain, and we are passengers riding on that fragile edge between expansion and collapse. In a way, the question of whether the universe will expand forever or one day contract feels like a mirror of our own lives. We don't know if things will drift further apart with no way back, or if, somehow, the gravity of what matters most will pull us back together. We live in that uncertainty, just as the universe does, moving forward without a clear answer, caught between endless possibilities, expansion without end, or a final, inevitable embrace. The expansion of the universe doesn't just push galaxies apart, it reshapes the very fabric of space-time itself. Imagine space-time as a vast, flexible sheet that everything, stars, planets, light, rests upon. As the universe grows, that sheet stretches in every direction. But unlike stretching a rubber band, this isn't something you can see or feel directly. It happens everywhere, all at once. The distances between galaxies grow not because they're moving through space, but because the space between them is expanding. And since space and time are deeply connected, woven into a single, inseparable entity, when space stretches, time itself is subtly altered, stretched along with it. This expansion influences everything from the paths light takes across the cosmos to how we measure time on grand scales. Light, for instance, travels through the fabric of space, and as the universe expands, the light is stretched along with it, becoming redder and less energetic over time. This is why the light from distant galaxies appears redshifted. Those photons have traveled across billions of years through an expanding cosmos, their wavelengths stretched like echoes fading as they move further from their source. It's as though light itself carries the memory of the universe's expansion, a story written in longer, slower wavelengths. Even time doesn't escape the influence of expansion. On the largest scales, time flows differently in regions separated by vast stretches of space-time. As the fabric expands, distant events drift farther apart not only in space but in the order of time itself, as if every clock is quietly whispering a slightly different story. Imagine standing on a shoreline and watching two waves ripple outward. As they grow farther apart, the rhythm of their pulses drifts, and even though they began together, they no longer align the same way. Time across the universe behaves like that, subtly pulled, reshaped, and scattered by the steady stretching of space. What's eerie is that there's no way to pause or reverse this stretching. The universe doesn't ask for permission. It doesn't slow to let us catch up. Even the forces we think of as constants, like gravity, become twisted within this shifting fabric. Gravity tries to hold things together, but expansion gradually pries them apart. It's like watching a rope slowly unwind. No matter how tightly you grip one end, the threads drift loose. One day, the expansion may become so extreme that even the bonds within atoms themselves won't be immune, unraveling the most basic structures of matter. And yet, here we are, suspended on this expanding sheet of space-time, drifting through the flow of moments that stretch and distort with the universe. On human scales, we don't notice the changes directly, just as a person aboard a raft floating on an endless river can't see how fast the current is moving unless they look at the distant shore. But everything we know, every star, every planet, every fleeting thought, unfolds on this restless fabric, forever in motion, shaped by the silent stretch of the cosmos. We live our lives on the edges of a universe that won't sit still, and though we can't feel the tug, we are part of that infinite drift, caught in a dance where time and space never stop expanding, never stop changing, and never circle back. When people hear that the universe is expanding, it's natural to wonder what it's expanding into. But the truth is stranger than any simple analogy. The universe isn't expanding into something else. It's not like a balloon inflating into empty space. Instead, space itself is unfolding from within. There's no edge, no boundary, no outside waiting for the universe to spill into it. Everything, every galaxy, star, atom, and ray of light, exists within the universe, and beyond it, there isn't an outside in any way we can understand. This is hard to wrap your head around because we're used to thinking of space as a container, like an empty room that things move through. But in reality, space is part of the universe's structure. It stretches and grows on its own, without needing any external backdrop. Imagine standing inside a dream that keeps expanding the longer you wander through it. The dream doesn't need anything outside it to exist. It creates its own space as it unfolds. The universe behaves in a similar way, growing from the inside out, with every point in space expanding away from every other point. No matter where you stand in the universe, it will always seem like expansion is happening all around you, as though you were at the center, but in truth, every place feels that way. There is no center, just an endless, growing field. This also means that asking what the universe is expanding into is a little like asking what's north of the North Pole. It's a question that only makes sense from our limited perspective. We're trapped inside space and time, and we can't step outside to take a look around. If there is something beyond the universe, it's beyond our ability to observe or even imagine in any meaningful way. It's not a vast emptiness waiting to be filled, but rather a complete absence of anything, even the concept of space itself. In the same way that time didn't exist before the Big Bang, there's no sense in which space exists beyond the universe. It's unsettling, in a way, to think that we live in a self-contained bubble of reality with no edge, no wall to press your hand against, no place to peek out and see what lies beyond. But it also makes the universe feel strangely intimate. Everything that exists, everything that ever was or will be, is contained within this growing fabric. We're not expanding into some great unknown. We are the expansion, part of this endless unfolding. Every moment, every atom drifting farther apart, is part of the same story, a story with no outside observer to witness it. This vastness, without boundaries or limits, is not just out there in the stars. It's the very thing that cradles our lives, quietly expanding with every breath we take, part of a universe that doesn't need anywhere to grow, only the freedom to keep becoming. It's easy to imagine galaxies moving apart like leaves drifting on a pond, carried away by a current. But the reality is more profound. What we observe isn't just objects shifting through space. it's space itself stretching between them. The key to understanding this lies in the light that reaches us from distant galaxies. As light travels across the universe, its wavelengths are stretched by the expansion of space, a phenomenon called redshift. The farther away a galaxy is, the more its light shifts toward the red end of the spectrum, not because the galaxy itself is moving through space at tremendous speeds, but because the space between us and the galaxy has expanded during the light's journey. This effect is baked into the light itself, as if the expanding fabric of space leaves fingerprints on every photon. If galaxies were simply moving through a static space, their speeds would follow a different pattern. Imagine cars speeding along a highway. The further you look, the more random the speeds might be, with no clear relationship between distance and velocity. But what we see with galaxies is strikingly different. Those that are farther away from us appear to be receding faster, in a smooth, predictable pattern. This is exactly what we'd expect if space itself were expanding, carrying galaxies along like dots on the surface of an inflating balloon. Each dot stays in the same place relative to its patch of surface, but as the balloon grows, the distances between them increase. Another clue comes from something called the cosmic microwave background, or CMB. This faint glow, left over from the earliest moments after the Big Bang, is scattered evenly across the sky. As space has expanded, the wavelengths of this ancient radiation have stretched along with it, cooling it to a temperature just above absolute zero. This uniform cooling only makes sense if the space itself has been expanding over billions of years, stretching everything it contains, even radiation. Even gravitational forces behave differently in an expanding universe. If galaxies were just flying apart, their mutual gravity would slow them down over time. But instead, what we observe is that the expansion is accelerating, meaning that the space between galaxies is not only growing but doing so faster and faster. This is not the result of galaxies moving independently, but of space itself stretching beneath them, making the distances grow without any local motion. In a way, it's like standing on an escalator that speeds up as you ride. It's not you moving faster. It's the ground beneath you pulling you along. What's fascinating, and a little unsettling, is that no matter where you stand in the universe, the expansion looks the same. Every observer, in every galaxy, would see the same pattern of redshift, the same fingerprints of stretching space. It's as if the universe has no center, and every point within it participates in this vast expansion equally. This isn't a simple drift or scattering of objects in an empty void. It's the very nature of space to expand, pulling galaxies apart like threads unraveling in a fabric that never ends. The idea that the universe's expansion is accelerating seems counterintuitive. If gravity pulls things together, why would the universe be expanding faster and faster? This is where dark energy enters the picture. It's not something we can see or touch, and we only know it exists because of the way the universe behaves. Think of dark energy as an invisible force woven into the very fabric of space, causing it to stretch more rapidly over time. Unlike gravity, which weakens with distance, dark energy appears to become more influential as space grows. The larger the universe becomes, the more space there is for dark energy to operate, pushing things apart with greater and greater force. The discovery of this accelerating expansion came as a shock. In the late 1990s, scientists expected to find that the universe's growth was slowing down over time, gradually pulled back by the gravity of all the matter it contains. But observations of distant supernovae, the explosive deaths of stars, revealed otherwise. The light from these ancient explosions was dimmer than expected, meaning they were farther away than predicted. This could only make sense if the universe's expansion had started to speed up at some point in the past, as if space itself had suddenly decided to grow faster. It was a puzzle no one saw coming, and the name dark energy was coined to describe whatever strange force was responsible for this cosmic acceleration. Dark energy behaves differently from anything else we know. It's not like matter or radiation that can be measured or collected. It seems to be an inherent property of space itself. As space expands, more dark energy emerges, fueling even more expansion in a self-reinforcing cycle. It's as if the universe is caught in a runaway process, where each moment of growth only accelerates the next, with no clear end in sight. This isn't a force pushing from the outside, but something embedded within the very structure of the cosmos, quietly urging space to stretch wider and wider. The unsettling part is that dark energy dominates the universe. Roughly 70% of everything that exists is thought to be dark energy, with only a small fraction of the total made up of ordinary matter, the stars, planets, and galaxies we can see. It's as if the universe is mostly composed of something we barely understand, a vast and invisible presence driving everything apart. What's more, the influence of dark energy might grow stronger over time. If it continues unchecked, galaxies that are now visible may eventually vanish from sight, carried so far away by the accelerating expansion that their light will never reach us. The universe could become a cold, empty place, with each galaxy trapped in its own isolated bubble of space, disconnected from all others. We don't yet know what dark energy really is. It could be a new kind of field, or something related to the vacuum energy of space itself. It might even hint at a flaw in our understanding of gravity on cosmic scales. But whatever it is, it seems to act like a quiet engine beneath everything, accelerating the universe's growth with a persistence that defies what we know about physics. It's a reminder that even though we've made incredible strides in understanding the cosmos, the universe still holds mysteries that stretch far beyond our grasp, expanding faster than our knowledge can catch up. Imagine looking up at the night sky, gazing into the stars, and realizing that what you're seeing is just a flicker of something much, much older. Now, if we could look beyond the stars, beyond the galaxies, and even further back in time, we would eventually reach a point where the universe was a very different place. The cosmic microwave background, or CMB, is like a fossil of that ancient universe, a remnant from a time when everything was still finding its place, just after the universe was born in a violent burst of energy we call the Big Bang. The CMB is significant because it's not just a faint glow in the background of the cosmos. It's the oldest light we can detect. It carries within it the story of how everything we know began to take shape. It was born when the universe was only about 380,000 years old, an unfathomably young age by cosmic standards. Back then, the universe was a dense, hot soup of particles, so tightly packed that even light couldn't move freely. Imagine a fog so thick that you can't see through it. This is what the early universe was like. As it expanded, it cooled, and at a certain point, particles combined to form atoms, allowing light to break free for the first time. That light is what we now see as the CMB. For us as humans, the discovery of the CMB in the 1960s was like finally hearing the faint echoes of an ancient conversation that the universe had with itself. It told us that the Big Bang wasn't just a theory but something that left behind evidence, woven into the very fabric of space. The CMB isn't just radiation. It's like a cosmic birthmark, proof that everything we see, every star, every planet, every galaxy, came from a singular, chaotic beginning. It's a message, traveling across billions of years, that reaches us now, whispering about a time when nothing resembled what we know today. The CMB is also eerily uniform, like the same melody playing across the universe, but there are tiny variations in its temperature, tiny differences in the warmth of this ancient glow. These imperfections are significant because they represent the seeds of all the structure we see in the universe today. Galaxies, clusters of stars, even the space between them, all trace their origins back to these subtle ripples in the CMB. Without them, the universe would have expanded into a smooth, empty void. The fact that we can study these imperfections gives us a window into how the universe grew from something small and simple to something vast and complex. For scientists and cosmologists, the CMB is like a map written in ancient light that shows how space-time itself has stretched and changed over billions of years. But for us, on a more human level, it's a reminder of our connection to the beginning of everything. It's as though the universe, vast and indifferent, holds within it a kind of memory, a soft, lingering trace of its own creation. And here we are, tiny specks in this immense, expanding cosmos, able to look back across time and understand a little more about where we came from, how everything we see emerged from a simple burst of energy that eventually became stars, planets, and life itself. The CMB, in its quiet, ancient glow, reminds us that we're all part of a story that stretches across the entire universe. In the early 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working on something completely unrelated to the origins of the universe. They were using a large antenna in New Jersey to study radio waves coming from outer space. But no matter where they pointed the antenna, they kept picking up a strange, persistent noise like a faint hiss in the background. At first, they thought it was interference, maybe from the city, maybe from the equipment, or even from pigeons nesting in the antenna. They tried everything to eliminate it, but the noise just wouldn't go away. What they didn't know was that they had stumbled onto one of the most important discoveries in the history of science. At the same time, physicists elsewhere had been working on a theory about the universe's early moments. According to this theory, the Big Bang would have left behind a faint afterglow, a kind of residual heat spread evenly across the universe. But no one had detected it. Penzias and Wilson weren't looking for this, but that persistent hiss they heard was, in fact, the very afterglow of the Big Bang, the cosmic microwave background radiation. This serendipitous discovery was proof that the universe began in a hot, dense state and has been expanding and cooling ever since. The CMB is that first light, released when the universe had just begun to cool enough for atoms to form, and it has been traveling through space ever since, stretching as the universe expands. What the CMB tells us about the early universe is as extraordinary as its discovery. It shows us that in those first few 100,000 years after the Big Bang, the universe was not filled with stars or galaxies, but with a hot, glowing plasma, particles of light and matter constantly colliding in a chaotic dance. It was an era before structure, before complexity, a time when the cosmos was nearly uniform in every direction. But tiny differences existed, and the CMB reveals them to us in astonishing detail. These subtle variations in temperature, only fractions of a degree, are like the cosmic seeds that eventually grew into galaxies, stars, and planets. Without them, there would have been no structure, no complexity, and no life. In a way, the discovery of the CMB connects us to the very fabric of time. It allows us to peer into the distant past, before the universe looked anything like what it does now. Imagine being able to see the universe not as it is, but as it was over 13 billion years ago, when it was still forming. The CMB is a kind of photograph of that time, frozen in its glow, telling us about the moment the universe became transparent, when light could finally travel freely through space. The discovery also brought humanity closer to understanding the origins of everything around us. It gave us a tangible piece of evidence that the universe had a beginning, and that beginning was not calm or quiet, but a violent explosion that gave birth to everything we know. For the first time, we had proof that the universe we live in was not eternal or unchanging, but had a story, a timeline, a progression from chaos to order. The CMB is not just radiation or light. It's a message from the universe's earliest days, speaking to us across the vastness of space and time, showing us how everything that exists today started from something incredibly simple, incredibly small, and incredibly powerful. It's strange when you think about it. How can something so vast, so impossibly distant, show such uniformity? The cosmic microwave background, spread across the entire universe, appears nearly the same in every direction we look. It doesn't seem to make sense at first. How could areas of the universe that are so far apart, separated by billions of light years, have almost the exact same temperature? The answer lies in an idea that stretches our imagination: the concept of inflation. Inflation suggests that, just after the Big Bang, the universe went through an unimaginably rapid expansion, growing faster than the speed of light for a fraction of a second. Before this, everything we see today, including the farthest corners of the universe, was much closer together. Close enough for all the particles and light to interact and share the same conditions, reaching an equilibrium of temperature. It's as if the universe was once a tiny, tightly knit neighborhood where everyone had the same experience. And then, suddenly, that neighborhood expanded at an exponential rate, pushing everything outward to the vast scale we see today. This inflationary period stretched out the temperature uniformity that existed when the universe was much smaller, spreading it across the cosmos. So, in a way, the uniformity we see in the CMB is a kind of frozen relic from a time when distances were minuscule. After inflation stopped, the universe continued to expand more slowly, and the light that had been trapped in the dense early plasma was finally able to escape. It's this light we see today as the CMB, still carrying with it that almost identical temperature from an era long gone. But there's more to it than just physics. In this incredible story of expansion and cooling, there's a sense of balance that feels oddly relatable to us. It's a reminder that, despite the vastness of space, the cosmos began as a single point, and every galaxy, star, planet, and person, was once part of the same shared origin. The uniformity of the CMB speaks to the idea that, at the most fundamental level, the universe strives for harmony, even as it expands into the unknown. We see the same temperature, no matter where we look, because the forces that shaped the early universe ensured that balance before everything scattered across unimaginable distances. Yet, the CMB isn't perfectly uniform. The slight differences in temperature, tiny ripples, are crucial, as they represent the seeds of all the cosmic structures we know today. Without them, the universe would have remained smooth and featureless. But these tiny imperfections, buried within the broader uniformity, allowed matter to clump together, forming galaxies, stars, and eventually life. It's like seeing a calm ocean from a distance. It looks smooth and even, but when you get closer, you notice the waves, the subtle movements that hint at something deeper. In the end, the uniformity of the CMB isn't just a physical curiosity. It's a snapshot of a moment when everything was connected, a quiet reminder that the universe, in all its vastness, was once small, unified, and balanced. And through the cosmic story of expansion and evolution, we're left with this glowing background, telling us how the universe once shared a common state, only to unfold into the staggering complexity we see today. As we've explored the cosmic microwave background, we've come to see it as a remarkably uniform imprint of the early universe, a kind of serene echo of the Big Bang. But when scientists took a closer look, they found something unexpected, like a subtle whisper beneath the harmony. A few peculiar irregularities that didn't fit neatly into the Big Bang model. These anomalies are rare, but they raise questions that shake the certainty we might feel about the origins of the universe. One of the most intriguing irregularities is something called the cold spot. When scientists mapped the CMB in great detail, they found this patch of sky that is significantly colder than the surrounding regions, a kind of cosmic bruise. It's not just a slight difference, but an area that seems unusually large and cold in comparison to the rest of the sky. While the Big Bang model predicts small variations in temperature due to the tiny fluctuations in the early universe, the cold spot stands out as something more extreme, something that doesn't quite fit the expected patterns. At first, this strange cold patch was thought to be a statistical anomaly, something that could have just happened by chance. But the more it's studied, the harder it is to ignore. Some theories suggest that the cold spot might be caused by a vast region of space with fewer galaxies and less matter, a kind of cosmic void that might affect the way light from the CMB reaches us. But even this explanation doesn't fully satisfy everyone. There's a lingering feeling that the cold spot could be hinting at something more fundamental, possibly even something beyond the Big Bang model itself. Another irregularity comes from the overall alignment of certain large-scale structures in the CMB, which scientists have nicknamed the axis of evil. It's an eerie term, but it reflects the strange and unsettling nature of this discovery. What they found is that some of the largest temperature fluctuations in the CMB seem to be aligned along a particular axis, as if the universe had some kind of preferred direction. This is deeply puzzling because the Big Bang model predicts that the universe should have no such direction. It should look the same in every way, no matter which direction you look. The existence of this axis challenges that assumption, raising the possibility that there might be deeper, unexplained forces at play in shaping the universe. These anomalies don't necessarily overthrow the Big Bang model. The model still explains so much about the history and evolution of the universe that it remains a cornerstone of cosmology. But these irregularities are like cracks in the surface, subtle signs that there might be layers of complexity that we have yet to uncover. They remind us that our understanding of the universe, even something as grand as the Big Bang, is always evolving, always open to revision. Every unexpected detail in the CMB invites us to look deeper, to question what we know, and to consider the possibility that the cosmos might hold secrets we haven't yet even begun to imagine. In a way, these anomalies are what make the study of the CMB so fascinating. They show us that the universe, like any great mystery, doesn't give up its answers easily. Even when we think we've found clarity in the afterglow of the Big Bang, there are still shadows, still oddities that pull at the edges of our understanding. The cold spot and the axis of evil serve as reminders that there's always more to discover, that the universe, in all its ancient light, still holds surprises for those who are willing to keep looking. In the earliest moments of the universe, there was no matter as we know it, only a dense, incomprehensibly hot state of pure energy. The birth of matter from this primordial energy is a story of transformation. one that mirrors the way all life begins with raw potential before it takes shape and form. As the universe expanded, it cooled down, much like the way molten rock eventually solidifies into something tangible. Within the first microseconds after the Big Bang, energy began to settle into more stable forms, and the basic building blocks of matter started to appear: quarks, electrons, and neutrinos. At first, these particles existed in a chaotic dance, colliding, interacting, and annihilating each other in the storm of energy. But as things cooled further, the quarks began to form groups, like scattered droplets merging to form larger pools. They bonded together to create protons and neutrons, which are the foundation of atoms. It was a delicate balance, like trying to mold something from clay that is just barely cool enough to hold shape. Any disruption, any excess heat, would undo the process. But it was in this precise moment, in these fractions of seconds, that the universe was beginning to craft the raw material from which everything else would eventually be born. Then came a pause, a cosmic silence lasting a few 100,000 years, a time when the universe continued to expand and cool, but the newly formed matter was still far too energetic to settle into anything recognizable. Protons and neutrons floated freely, unable to bond with electrons to form atoms because the universe was still too hot for them to link. It was like watching pieces of a puzzle hover, each piece aware of its place but unable to connect just yet. Eventually, the temperature dropped enough for electrons to finally find their partners. They began to orbit around protons, and hydrogen, the simplest atom, came into existence. It's fascinating to think that the entire universe was once in a phase where everything, every person, every star, every planet, was just potential. Hydrogen atoms, tiny and simple, were the first structured forms, and they became the seeds from which stars, galaxies, and life itself would eventually grow. The story of matter's formation is one of incredible patience. It didn't all come together in an instant. Over millions of years, gravity began to pull these atoms together, compressing them into massive clouds. Within these clouds, under immense pressure, hydrogen atoms fused together to form helium, igniting the first stars in brilliant bursts of light. And from these stars, heavier elements were born, scattered across the cosmos in supernova explosions, enriching the universe with the ingredients for planets, oceans, and living beings. It's almost poetic to consider that the atoms in our bodies were once forged in the hearts of stars, that the same matter that formed in those first moments after the Big Bang now makes up the cells in your body. From chaos and energy, the universe gave rise to structure, and from that structure, complexity and life itself. The matter around us is not just a random occurrence but a testament to the enduring nature of creation, a reminder that even from the simplest of beginnings, something beautiful and intricate can arise over time. In the earliest days of the universe, there was only energy, a chaotic, searing light stretching in all directions. It was a universe in flux, a place where nothing solid could exist, not yet. But like the way humans seek out stability in the midst of chaos, this energy began to slow and cool, creating the conditions for something new to emerge. The first atoms, which now seem so fundamental to our existence, were not born easily. They emerged from a delicate balance between the primal forces at work in that early cosmic storm. As the universe expanded, it cooled, and with this cooling came a moment of stillness. Out of the energy, particles like protons and neutrons began to form, but these weren't yet atoms. They were like puzzle pieces, waiting for the right conditions to find their counterparts. These particles, so essential to the creation of atoms, were on their own for a long stretch of time, unable to connect with the electrons needed to complete their structure. The universe was still too hot for them to interact meaningfully. Electrons darted wildly, untethered, as if everything that could connect was being kept apart by an invisible barrier. It wasn't until around 380,000 years after the Big Bang that the universe cooled enough for something miraculous to happen. The energy had finally dissipated enough that the free-floating electrons could slow down and begin to bond with protons. This was not an instant event, but rather a gradual process, like waiting for a complex mechanism to fall into place piece by piece. The simplest atoms, hydrogen, were born when these electrons found their orbits around the protons, creating a kind of cosmic harmony. For the first time, stable, neutral atoms could exist, tiny building blocks that would go on to shape everything we know. The creation of these first atoms wasn't the end of the story, but the beginning of a new phase of the universe's journey. Hydrogen, while simple, became the essential ingredient for everything that would come after. These atoms floated through space, gathering in clouds, slowly pulled together by gravity. And within those clouds, under pressure, they ignited the first stars, which would become the factories for all the other elements. What's particularly moving about this process is that, in a sense, the atoms that make up the very fabric of the universe, and us, were created in moments of balance and connection. Just like human lives are shaped by meaningful relationships, by coming together at the right time. The universe itself was built on these small but crucial moments where particles finally found each other. Without that, nothing we know would exist. Not the stars, the planets, the water, or even life. Atoms are small, invisible to the naked eye, but they represent the very essence of creation. They began as energy, transformed through a slow, almost patient process into the fundamental parts of everything. That simple hydrogen atom, formed in the quiet moments after the chaos, is where the story of matter and life truly begins. From those first atoms, all the complexity of the universe grew, reminding us that even the smallest things, given enough time and the right circumstances, can lead to something extraordinary. The universe didn't start out with galaxies, stars, or planets carefully arranged in the patterns we see today. In its infancy, everything was spread out as a nearly uniform sea of particles and energy, but even in that apparent sameness, small imperfections existed. It's these tiny, random fluctuations in the density of matter that set the stage for how galaxies, stars, and planets would eventually come to be scattered across the cosmos. Think of it like a vast landscape of possibilities. Some areas just had slightly more potential to shape the future than others. As the universe expanded, gravity began its work, pulling on those slight imperfections, drawing matter toward areas where it had gathered just a bit more densely. It's a slow and deliberate process, one that stretches across eons. Gravity acts like a sculptor, patiently pulling together clouds of gas and dust into the formations that would eventually become galaxies. It's as though the universe was sowing seeds, but those seeds would grow into stars and planetary systems over the course of billions of years. It wasn't an orderly process, though. Matter didn't just gather into perfect, evenly spaced shapes. It was a struggle, a kind of cosmic tug-of-war, where some regions were drawn tightly together while others remained sparse and empty. The galaxies themselves, these grand collections of stars, were the result of that gravitational clustering. As they formed, their shapes and structures, spiral, elliptical, irregular, were influenced by countless factors. The rate of rotation, the density of material, the interactions with other forming galaxies. Some galaxies collided and merged, altering their paths and shapes in chaotic ways. Just as human lives are shaped by the random meetings and interactions with others, so too were these galaxies shaped by their cosmic neighbors, sometimes tearing each other apart, sometimes combining into something entirely new. Within these galaxies, the stars and planets took their places. The stars were born in dense clouds of gas and dust, collapsing under their own gravity until nuclear fusion ignited within them, lighting up the dark spaces of the universe. Some stars formed in clusters, others alone, but they all shared a common origin: the gathering of matter under gravity's influence. Planets, in turn, formed from the leftover debris around these stars, material that coalesced into rocky worlds or gas giants. Each system, each planet, found itself in a unique position, shaped by the specific conditions of its own birth. What makes this distribution of galaxies, stars, and planets so human in its complexity is the way randomness and inevitability played together. There was no grand blueprint dictating where every galaxy would form or where every planet would end up. Yet there was an order to it all, driven by the fundamental forces of nature. It's as if the universe, while unpredictable in detail, still follows certain rhythms and rules, like the way the contours of human lives are influenced by both chance and the deep-seated needs that drive us. The universe's structure, then, is not a neat, predetermined grid but rather a vast, dynamic web, where galaxies and stars are distributed unevenly, with clusters in some places and vast voids in others. This unevenness is part of what makes the cosmos so rich and varied. The galaxies that formed billions of years ago are still moving, still drifting apart as the universe continues to expand. reshaping the grand structure of space itself. The stars that light up the night sky, the planets we dream of visiting, all of them are scattered across a vast, changing landscape, their positions dictated by a delicate interplay of forces that began in the earliest moments of the universe but continue to act even now. When we look out into the universe and marvel at its stars, galaxies, and clusters, we're seeing only a small fraction of what's truly there. The majority of the universe is composed of something far stranger: dark matter and dark energy, forces that don't reveal themselves through light, but rather through their profound influence on everything we can see. These invisible forces act like unseen hands, guiding and shaping the large-scale structure of the universe, even though we can't directly observe them. Dark matter plays a key role in the formation of galaxies and the vast cosmic web that connects them. It's not like the matter we're familiar with. It doesn't emit light, interact with electromagnetic forces, or clump together to form stars and planets. Instead, it exists as a vast, invisible scaffold that permeates the universe. Imagine trying to build a house without being able to see the frame holding it together. That's the role of dark matter. It provides the unseen framework that allows galaxies to form and cluster. Without dark matter, the galaxies we know wouldn't have had enough gravitational pull to come together. Ordinary matter alone wouldn't be enough. It would be too diffuse, too scattered. In the early universe, dark matter began to clump together long before visible matter could. These clumps, or halos of dark matter, acted like gravitational wells, pulling in gas and dust that would eventually form stars and galaxies. Think of dark matter as a silent architect, laying down the foundation for all the structures we now observe. Galaxies formed within these halos, drawn together by dark matter's gravity. Even though we can't see dark matter, we feel its presence through the way it bends light around massive structures and the way it shapes the rotation of galaxies, making them spin faster than they should based on the visible matter alone. While dark matter helps bind the universe together, dark energy has the opposite effect. It's driving the universe apart. This mysterious force is pushing galaxies away from each other at an accelerating rate. For much of cosmic history, dark matter dominated, allowing galaxies to form and cluster. But as the universe expanded, dark energy began to take over, pulling space itself apart. It's a bit like watching two opposing forces at work: dark matter pulling inward, dark energy pushing outward. In the grand scheme of things, dark energy plays a role in shaping the future of the universe's structure. The farther away galaxies are, the faster they're moving away from us, thanks to dark energy's influence. Over time, this expansion will stretch the fabric of the universe so much that galaxies will drift further apart, and eventually, if dark energy continues to dominate, the universe could become a place where galaxies are so far separated that they no longer interact. The cosmic web that dark matter helped create might unravel as dark energy continues to push everything apart. The interplay between dark matter and dark energy is like a cosmic balancing act, though not in harmony. One is the creator, binding and forming, while the other is the destructor, expanding and dispersing. Yet both are necessary to understand the universe's structure. Without dark matter, there would be no galaxies, no stars, no planets. Without dark energy, the universe wouldn't be expanding as it is, and the distant future would look very different. Even though we can't touch or see dark matter or dark energy, they are deeply intertwined with the very fabric of existence. They are the forces that sculpted the universe, not in the visible ways we often focus on, but in the hidden, foundational layers that shape everything from the smallest stars to the largest galaxy clusters. It's a reminder that the universe is far more complex and mysterious than what we can see with our eyes, and that the unseen often holds the greatest power in shaping reality. The human mind, bound by the constraints of existence, struggles to grasp concepts that defy the very framework of reality we rely on. Time, as we experience it, is deeply intertwined with the way we move through the world, from the rising and setting of the sun to the beat of our hearts. It seems omnipresent, linear, and unyielding, guiding every moment of our lives. Yet, when we turn our thoughts toward the origins of the universe, toward the cosmic event we call the Big Bang, time itself begins to unravel, slipping from our grasp like sand between fingers. Before the Big Bang, it is said that there was a singularity, an infinitely small point where all the matter, energy, and forces of the universe were condensed. But to speak of before the Big Bang raises a paradox, a human contradiction. For us, every experience, every thought, every breath exists within the flow of time, and our language is steeped in it. The concept of before carries the assumption that time already exists, that there is a when that precedes the moment of creation. And yet, the very nature of the Big Bang defies that assumption. Time, as we know it, came into being at that moment. The singularity that gave birth to the universe did not occur in time. It created time. It's almost as if we are standing at the edge of a great precipice, looking out into a void where time itself dissolves. It's disorienting. We want to ask, what was there before? Could there have been a before? But the answer is that these questions dissolve into nothingness. Time and space, the fabric that weaves together the cosmos, emerge together in the same moment. To ask if time existed before the Big Bang is like asking if there was a where before space existed. It is a question that crumbles under the weight of its own assumptions. Yet, we are human, and we seek stories. We long for beginnings, middles, and ends, narratives that allow us to find meaning in a universe that feels so vast and indifferent. Our minds crave a cause and effect, an order to things, so the idea that time itself is something that could begin, that could be born out of nothingness, feels unsettling. We want to impose the familiar on the unknown, but the cosmos does not bend to our desires. Time, in its essence, is part of the universe, just as space is. There was no ticking clock in the background, waiting for the cosmos to burst into existence. No endless corridor of time stretching backward, waiting for something to happen. To contemplate the origins of time is to confront the limits of our understanding, to feel the weight of the unknown pressing down on us. But perhaps, as humans, this is where our greatest strength lies. Not in having answers, but in the willingness to question, to explore those boundaries. Our experience of time, this orderly march from past to present to future, is but one sliver of a greater reality, a deeper mystery where time itself is both the question and the answer. The human element here is our struggle against the intangible, our relentless curiosity, and the deep, almost existential discomfort that arises when we peer into the void and see not a clear path, but the infinite unknown. What does it mean to live within time, knowing that it is but a construct of the universe itself, that we are creatures born of time, but the reality we inhabit might not hold the same truths we cling to? It's a question that lingers, haunting our thoughts, a reminder that no matter how much we learn, the deepest mysteries of the universe remain just out of reach, inviting us to wonder, to search, and perhaps never to fully understand. It's strange to think about the world we inhabit, with its spaces to move through and its clocks ticking away the moments, as something that didn't always exist. Space, that endless expanse we live in, and time, that steady current we ride, weren't always there. They emerged from a singularity, a point that defies all our instincts, a place where the laws of physics, the ones that govern every step we take, every breath we draw, break down completely. We're so used to thinking of space and time as the stage on which everything happens. But before the universe, before that first moment of creation, there was no stage. It's almost incomprehensible. When we try to picture the singularity, it's like trying to imagine something so concentrated, so dense, that it doesn't have dimension or duration. There's no before, because there's no time to define it. No outside, because space hasn't unfurled yet. In this infinitesimal point, reality is packed tighter than our minds can hold. And then, somehow, that point, this singularity, undergoes an unimaginable transformation. It's not an explosion in the way we think of explosions, with things bursting outward into a pre-existing environment. Rather, the very fabric of what we would come to know as space begins to stretch, like an artist with a blank canvas, except there was no canvas before. It comes into being as the paint touches it. Space wasn't waiting to be filled. It was the act of creation itself. Time emerges in a similar way, not as something that starts ticking in the background, but as part of the unfolding. For us, time is this constant, this inevitable forward motion. But in those earliest moments, time wasn't yet fixed in the way we understand it. It was raw, fluid, taking shape as the universe itself expanded. There was no flow of time before this, just a formlessness, an absence that we can only describe by what it wasn't. And then, almost in the same breath, there is space for things to happen and time for them to happen in. What's perhaps even more unsettling for us as humans is the realization that the rules we rely on, the cause and effect, the structure of reality we navigate every day, didn't exist before this moment. The singularity, this primordial seed of the universe, followed a logic that we may never fully understand. It challenges our need for order, for answers that make sense in the context of our experience. But at the heart of this mystery is a process that set everything into motion, not just matter and energy, but the very structure that allows events to unfold. It's as if we're standing at the birth of not just a universe, but of possibility itself. The space that emerges is not simply a place for objects to float around in. It's the very condition for anything to exist at all. And time, with its arrow pointing relentlessly forward, is the medium through which change can happen, through which the universe can evolve, stars can ignite, and life can one day emerge. In some ways, it's terrifying. We, as creatures bound by this universe, look for origins, for solid ground to stand on, and yet space and time themselves are the result of a process that we can barely describe, much less understand. Our existence is wrapped up in this event, in the emergence of the very dimensions in which we live. Every moment we experience is a ripple from that first great unfolding, and yet we are left with the unsettling truth that it came from something utterly foreign, something that defies all we know. And though we are creatures of space and time, we're left with the deep realization that these things are not as fundamental as we once thought. They had a beginning, and with it, the story of everything began. The nature of time, the way it quietly threads through our lives, is something we rarely question. We wake up, move through our days, and feel its presence like an invisible pulse that orders everything. But when you try to imagine a universe where time didn't always exist, it's like trying to hold on to something that slips through your fingers. Time feels like an intrinsic part of reality, something as natural as the air we breathe. Yet, the deeper we dig into the fabric of the universe, the more we begin to realize that time itself may be nothing more than a consequence of the Big Bang, a property that came into being the moment the universe did. Before that first instant, the singularity, it wasn't just that there was no universe as we know it. It was that there was no framework for anything to happen at all. We think of time as something that passes, but in a very real sense, it only started passing when the universe began to unfold. There was no ticking clock, no before to hang your thoughts on. The Big Bang wasn't just the explosion of matter into a void. It was the birth of the conditions that allow for existence itself. Time, as we experience it, is part of those conditions. It is woven into the very fabric of the cosmos, inextricably linked to space itself, as though they are two sides of the same coin. If you strip away the human experience of time, our days, hours, seconds, you're left with something more fundamental, something that feels almost alien. Einstein's theory of relativity gives us a glimpse into this truth. Time isn't some universal constant that ticks along, indifferent to everything else. It stretches, it warps, it bends with the pull of gravity and the speed of motion. In the early moments after the Big Bang, time didn't behave the way we're familiar with now. In fact, it's hard to say that there was any meaningful passage of time at all in those first fractions of a second. Time as a steady, flowing river is something that emerged as the universe cooled, expanded, and formed into the structures we know. Galaxies, stars, and eventually us. For us, time is personal. It shapes the narrative of our lives, marking the past, present, and future. But when you zoom out to the level of the universe, time becomes something far more fluid, a property that depends on the very structure of the cosmos. The question of whether time existed before the Big Bang almost doesn't make sense, because the Big Bang is what gave rise to time as we understand it. Without the space to contain events, without the movement of matter and energy, time has no meaning. It doesn't exist as an abstract entity floating in some eternal void. It's part of the framework that defines reality. The Big Bang didn't happen in time. It created time. For us, this might feel unsettling. We live in the flow of time, and it feels as real as the ground beneath our feet. But if time is just another property of the universe, born alongside the stars and planets, what does that mean for our place within it? It suggests that time, like everything else, has its own cosmic history, a beginning tied to the birth of the universe itself. And if time had a beginning, what of its end? Will it eventually stop, unraveling alongside the fabric of the universe, or will it stretch on into infinity, carrying us with it? The human element here is our deep connection to time. It is the rhythm of our lives, the silent companion to everything we do. And yet, the truth of time is far stranger than anything we could have imagined. It's a reminder that the universe, in its vast complexity, doesn't always align with our intuitive sense of things. Time, in all its personal importance, is just one more thread in the grand tapestry of existence, pulled from the same singular moment that gave birth to everything. It's a consequence of creation, a property of the universe that shaped not just the cosmos, but the very essence of our lives, pulling us forward through the unknown, moment by moment. In the unimaginable furnace of the early universe, space-time itself was far from the calm, predictable stage we experience now. We think of space and time as solid, dependable things. Space is where objects exist, and time is the flow that carries events forward. But in those first moments after the Big Bang, the conditions were so extreme that even space and time became something else, something fluid and unstable, bending and stretching in ways that defy our intuition. It's almost as if space-time, the very fabric that holds everything together, was molten, shifting under the pressure of temperatures and energies that are far beyond anything we can recreate or even fully comprehend. In that chaos, the four familiar dimensions, three of space and one of time, weren't yet fully formed. They were emerging, trying to settle into a structure that could support a universe, but in those first fractions of a second, they were in a state of flux, unpredictable and raw. The smooth, flowing space-time that we experience now was in turmoil then, warping violently under the intense gravitational forces that existed at those scales. At such extreme conditions, quantum effects and gravity collide, and the rules we've come to know, those that govern planets, stars, and even the fabric of space-time, don't hold. Everything, from the smallest particles to the entire cosmos, is governed by a kind of quantum chaos where probabilities reign, and nothing is certain. Space-time, rather than being a passive backdrop, becomes an active participant in this strange cosmic dance. Gravity, which is tied to the shape of space-time, acts so intensely that even the concept of distance, of separation between points in space, begins to break down. Time, too, loses its grip on the orderly progression of past, present, and future. In those moments, the boundary between what we think of as space and what we think of as time blurs. For us, living in this gentle, cooled-down version of the universe, it's hard to imagine such a reality. Time for us is this steady, unchanging march forward, and space is a vast expanse, indifferent to what happens within it. But at the extreme conditions of the early universe, space-time was alive with possibility and uncertainty. It was in a state of becoming, and with each passing fraction of a second, it evolved, slowly cooling, stretching out, and stabilizing into the framework we know today. And yet, in a way, we are still connected to that chaotic moment. The universe has expanded and evolved, yes, but those early conditions left imprints, echoes of that raw beginning, still visible in the cosmic microwave background, the faint afterglow of creation. It's as if space-time itself still remembers that brief period when it was anything but predictable, when the forces shaping it were beyond comprehension, and its very existence was in flux. For us as humans, it's almost impossible to imagine a reality where the rules are so different, where space and time themselves are not constants but variables that can warp, stretch, and even lose their meaning. We are beings who move through the universe with the certainty that space is there, and time will keep flowing. But in those extreme conditions, even those certainties fade, leaving us to wonder what it means to exist in a universe where the foundations of reality are as mutable as the events they contain. It's a reminder that the cosmos, at its core, is far stranger and more mysterious than we can easily grasp, and that even the things we take for granted, space, time, existence itself, are shaped by forces and conditions beyond our wildest imaginings. There's a strange comfort in thinking of space and time as infinite, like two endless rivers stretching on forever, their flow carrying us along with them. Infinity feels like it should offer certainty, a kind of permanence that reassures us. But when we look deeper, when we examine the universe not just as it seems to us, but as it really is, that certainty begins to fray. Are space and time truly infinite? Or are they bound, finite, with beginnings and perhaps even ends? It's a question that gnaws at the edges of our understanding, one that forces us to confront the limits of what we can know. Space feels vast, overwhelming even, But that doesn't mean it's without limits. In fact, the universe has an edge, not in the way you might imagine an edge where space simply drops off, but in the sense that space itself is expanding, creating more of itself as time moves forward. And here's where things start to get unsettling. If you trace that expansion back, you eventually arrive at a beginning. The Big Bang wasn't just the birth of matter and energy, it was the moment when space itself began to expand. This suggests that space is not infinite in the way our minds might long for it to be. It had a beginning. It might even have an end, depending on how the universe continues to evolve. Will it keep expanding forever, stretching into some cold, endless future? Or will it one day collapse back in on itself, bringing space to an end just as suddenly as it began? Time, too, carries this unsettling quality. Our experience of time, this constant flow from one moment to the next, seems to promise an endless continuation. We live as though time stretches forward into infinity, but the past tells a different story. Time had a beginning, tied intimately to the birth of the universe itself. Before the Big Bang, there was no time, at least not as we understand it. This forces us to confront the uncomfortable fact that time, like space, is not eternal. It started at that singularity, that moment of creation, and just as it had a beginning, it might someday have an end. If the universe expands infinitely, time may continue to stretch forward. But if the universe collapses or reaches a state of heat death, time as we know it could cease to have meaning. For us, humans bound by space and time, this is deeply unsettling. We experience our lives within these dimensions, navigating the world through space and aging through time. The idea that they could be finite, that they had a beginning and might have an end, challenges the way we think about existence itself. What does it mean to live in a universe where the very framework that holds everything together is temporary, where even time, the constant companion of our thoughts and actions, is something that could one day fade away? But there's a strange beauty in this realization too. The finiteness of space and time doesn't diminish their vastness or their importance. It only makes them more precious, more fleeting. It ties us to the universe in a way that feels both profound and humbling. We are not just inhabitants of space and time. We are part of their story, creatures born from the same moment that created the stars, the galaxies, and the very fabric of reality itself. And if that fabric had a beginning, then everything we experience is a consequence of that moment, rippling outward through the cosmos. So, are space and time infinite? In some ways, they stretch far beyond what we can comprehend, but they are bound by the same forces that shape the universe. They had a beginning. And if they had a beginning, perhaps they are not as infinite as we once thought. Perhaps the true mystery lies not in their infinite nature, but in the way they came into being, the way they hold us in their grip, and the way they may one day release us into something beyond time, beyond space, beyond everything we think we know. The singularity, in the context of the Big Bang model, represents a moment in the universe's history where everything that exists now, every star, planet, atom, and even time itself, was condensed into an unimaginably small point. It wasn't just dense matter. It was a point where the known laws of physics ceased to function, a place where infinity and zero seemed to collide. Space as we understand it didn't exist. Time didn't flow. The universe was essentially trapped in a paradox, existing in a state of pure potential. Imagine, if you will, standing on the precipice of creation itself, looking into an abyss not of darkness or void, but of pure everything. All the forces of nature, the fundamental particles that form every bit of matter, and the very fabric of space-time were fused in this singular point. But this isn't something you could see, touch, or even properly imagine. It's like trying to grasp a moment before a thought forms in your mind, a point before the universe even had a place to be. Then, in an instant, an event so sudden and profound that it escapes normal language, this singularity expanded. Not like an explosion, but an unfolding, a release. Time began to tick forward. Space stretched outward. The universe as we know it started its grand journey from simplicity to complexity. In that moment, reality bloomed from that singular, unknowable point into the cosmos we inhabit today. To think about it from a human perspective is like tracing your entire life back to a single heartbeat in the womb. Only in this case, that heartbeat carried the potential for stars, galaxies, and life itself. The singularity is the ultimate beginning, a moment that contained everything while appearing as nothing. It's the most profound mystery, the source of our shared existence, and yet, it lies forever just beyond the reach of human understanding. Physics, as we know it, begins to unravel when faced with the singularity. Our best theories, the ones that have helped us understand everything from the motion of galaxies to the behavior of subatomic particles, simply can't cope with the extremes present there. At the heart of this problem lies a conflict between two of our most powerful tools for describing the universe: general relativity and quantum mechanics. General relativity, which describes gravity and the structure of space-time, treats the singularity as an infinitely small, infinitely dense point. But infinity is a troubling concept in physics. It suggests that something has gone wrong, that our equations are no longer giving us a meaningful description of reality. When we try to understand what happens in such a place, the very fabric of what makes sense in the universe begins to tear apart. Gravity becomes so intense that it bends space and time in ways we can't follow. Time, distance, size. These concepts lose their usual meaning. Even the very notion of cause and effect could break down, which makes it impossible to predict or describe events inside the singularity. The quantum world, with its strange rules and uncertainties, doesn't neatly apply here either. In that tiny point, quantum effects and gravitational forces both become so strong that they fight for control, creating a paradox where neither theory can fully take over. The human desire to understand such a place pushes us beyond the limits of current physics, and yet, for now, we're left with a deep gap in our knowledge. It's a reminder that while we've made tremendous strides in understanding the cosmos, there are still realms where nature keeps its secrets, defying even our most advanced thinking. It's like trying to solve a puzzle where some of the pieces are missing or don't even exist yet. In many ways, the singularity stands as a boundary between what we know and what we still must discover. It's where the universe itself asks the biggest question, and so far, we can only stand on the edge, peering into the unknown. The idea that the singularity might be a quantum phenomenon is intriguing because it opens the door to a reality where classical physics simply isn't invited. At that point of creation, the rules that govern the large-scale universe, like gravity, which holds planets and stars in place, are swallowed by a much stranger, smaller set of rules. Quantum mechanics, the framework that describes the subatomic world, works in probabilities, uncertainties, and interactions that defy common sense. It suggests that, at incredibly tiny scales, things don't behave the way we expect. Particles can be in multiple states at once, distances and times blur together, and reality becomes more fluid than fixed. If the singularity was governed by quantum laws, it wouldn't have been a smooth, deterministic point, but something far more complex and chaotic. Time and space, instead of existing as well-defined entities, might have fluctuated wildly, perhaps even appearing and disappearing in strange, unpredictable ways. The singularity could have been an intensely quantum object, a sort of cosmic storm of probabilities and uncertainties, where all the forces and particles were jumbled in an unfathomable dance. For us, as humans, this kind of universe is almost impossible to visualize. It's like trying to imagine a place where up doesn't necessarily mean up, and where events don't unfold in any sort of orderly timeline. If the singularity was a quantum event, it wasn't the kind of solid, unchanging thing we're used to picturing when we think of the origins of the universe. Instead, it might have been a bubbling froth of potential, waiting for something to tip the balance and allow the universe to expand, space to stretch, and time to begin flowing. In this way, the quantum world may hold the answers to the biggest questions about the singularity. It's a realm where logic twists and shifts, where possibilities are more real than certainties, and where the seeds of everything that exists now could have been contained within that chaotic quantum soup. The singularity of the Big Bang and the singularities found at the heart of black holes are both points where the laws of physics crumble, but they lead in very different directions. In a black hole, matter collapses inward under the intense pull of gravity, compressing everything into a point of infinite density. It's a dead end, a place where space-time bends so sharply that not even light can escape. From the outside, it seems like everything falls into a void, and anything crossing the event horizon is lost to us forever. The Big Bang singularity, on the other hand, is not a collapse but an emergence. Instead of being a point where everything is drawn in, it's a point where everything flows outward. The singularity at the start of the universe wasn't a trap, it was the origin of everything. Time and space themselves expanded out from this moment, carrying all matter and energy along with them. While black hole singularities pull everything into an unknowable state, the Big Bang singularity pushed everything into existence. Yet, there's a strange symmetry between them. Both represent the limits of our understanding, where density becomes infinite and time seems to behave in ways we can't comprehend. Some even theorize that a black hole singularity could be connected to another universe, almost as if what falls in might emerge elsewhere. This has led some to wonder whether the Big Bang itself could have been the result of such a process, a universe birthed from a singularity in another, older cosmos. For us, as beings bound to this universe, it's fascinating and unsettling. A black hole singularity is a one-way journey inward, a place of ultimate collapse. The Big Bang singularity is the opposite, an outward explosion of potential. In both cases, they hint at realities beyond our grasp, where the rules we rely on fall away, leaving behind only questions about what lies beyond. Dark matter and dark energy are like the silent characters in the cosmic story. They are vast, invisible forces shaping the universe in ways we can't directly see. Yet their influence is undeniable. Imagine standing in a park, looking at the stars. Everything visible, the trees, the air, even your own body, is made of atoms. But you know there's something more, something that lies beyond your senses. That's where dark matter comes in. It doesn't emit light, doesn't reflect it, doesn't interact with anything in a way that we can easily detect. Yet, it's all around us, influencing the way galaxies move and even the way the universe expanded after the Big Bang. Now think of the Big Bang not as an explosion, but as a rapid expansion of space itself, like stretching the fabric of the cosmos from an unimaginably small point into something vast and intricate. In those first few moments after the Big Bang, everything was incredibly hot, dense, and chaotic. Matter was jostling about, particles colliding, energy swirling. As the universe cooled, particles began to slow down and coalesce, forming atoms, stars, and eventually galaxies. But here's the strange thing. When scientists began to study the way galaxies moved, they found something unexpected. There wasn't enough visible matter to account for the way galaxies were holding together. If it were just the visible matter, galaxies should have been flying apart, spinning out of control. But they weren't. Something unseen was providing the extra gravitational pull to keep them together. That's dark matter. It's like being in a crowded room where you can only see a fraction of the people, yet the whole room feels packed. You can feel their presence even if you can't spot them. Dark matter, similarly, makes up about 27% of the universe's mass and energy. It was there from the beginning, woven into the fabric of space and time, shaping the cosmic web that galaxies formed along. Without dark matter, the structures we see in the universe wouldn't exist as they do today. Then, there's dark energy, the even more mysterious counterpart to dark matter. If dark matter is the glue holding galaxies together, dark energy is the force pushing them apart. In the late 1990s, astronomers discovered that the universe wasn't just expanding, it was accelerating. This was a huge surprise. You'd think that after the Big Bang, the universe would eventually slow down in its expansion, much like a ball thrown into the air eventually falls back to the ground. But instead, the universe is speeding up, like something is stretching it faster and faster. This accelerating expansion is driven by dark energy, which accounts for roughly 68% of the universe. We don't know exactly what it is, but it's like the universe has this constant pressure that pushes everything apart. It's quiet, subtle, but relentless. The space between galaxies is getting bigger and bigger, and in billions of years, distant galaxies might be so far away that we can't see them anymore. Now, picture someone sitting by a campfire, staring at the flames. There's the heat from the fire, the warmth, the light. But just beyond the circle of light, there's the vast unknown, the dark woods stretching out into the night. You know there's more out there than what you can see, and that's what makes it mysterious. That's what dark matter and dark energy are. This invisible part of the universe that we sense, that we know is out there, but that we can't fully understand yet. They're as much a part of the universe's story as the stars themselves, yet their chapters are still being written. It's hard to grasp that the universe itself is expanding, even more so that it's speeding up. To wrap your head around dark energy, you have to think about the universe as something living, not static. Imagine being in a room that's constantly getting bigger, with the walls moving farther and farther away from you, but you can't feel or see what's causing it. Dark energy is the invisible force driving that expansion, pushing galaxies apart faster as time goes on. It's not something we can touch or see, but its effects are everywhere when we look at the cosmos. Back in the early 20th century, scientists thought the universe might be slowing down after the Big Bang. It made sense. Throw a ball into the air, and it eventually stops, right? Gravity pulls it back down. The universe, with all its mass, should have been slowing in its expansion due to the gravitational pull of all the matter in it. But when astronomers started measuring distant supernovae, massive explosions that serve as cosmic lighthouses, they noticed something unexpected. These supernovae were farther away than they should have been, suggesting the universe wasn't just expanding, it was speeding up. This was like standing on a hill and watching someone throw a ball into the air, only to see it pick up speed and disappear into the sky. It defied logic. What could possibly be causing this? The answer, or rather the name for the unknown force, was dark energy. But giving it a name doesn't mean we understand it. Dark energy makes up about 68% of the universe, yet we don't know what it is. It's like knowing there's a wind that blows, but never being able to feel it on your skin. To add another layer of strangeness, dark energy doesn't act like normal forces do. With gravity, you'd expect things to pull together, but dark energy does the opposite. As the universe grows, dark energy seems to get stronger, stretching space itself. Imagine you're watching two people standing on a street, slowly walking apart. As time goes on, not only are they drifting away from each other, but something is accelerating their movement, making them run faster in opposite directions. That's what dark energy does to galaxies. The distances between them are growing, not just steadily but more and more rapidly, as if some invisible hand is pulling the universe apart. We live in a time when galaxies are still visible to us, when light from these distant stars and worlds is still reaching us. But as the expansion continues, in billions or trillions of years, many galaxies will recede beyond our sight. The universe will be so stretched that light from these distant places will never reach us. The night sky will look different, a lot emptier. It's a lonely thought, this idea that dark energy is quietly working, spreading things out over unimaginable distances, separating the cosmic family of galaxies. In some ways, dark energy is like a clock winding down the universe. Every tick drives things farther apart, makes the universe a little more isolated. While we can't see dark energy directly, we see its consequences, feel its presence in the data we collect from the sky. It's a reminder of how much of the universe remains beyond our understanding, a force we can't predict or control, yet one that shapes the very fabric of existence. If you imagine the universe as something that holds together like a delicate tapestry, then the idea of a big rip is the nightmare that haunts that fabric. Dark energy, with its mysterious ability to stretch space, could one day pull too hard on the threads that tie everything together. The notion of a big rip is based on the idea that dark energy might not just keep accelerating the expansion of the universe, but it could grow so strong that it eventually overcomes all forces, gravity, electromagnetism, even the bonds that hold atoms themselves together. Imagine standing on a quiet beach, watching the tide slowly but surely rise. At first, the water seems calm, like it will never reach you. But as time passes, you realize the tide is relentless, moving faster than you expected. In this analogy, dark energy is that rising tide. If it keeps growing unchecked, the consequences could be catastrophic. At first, it would be galaxies that get pulled apart. They're already drifting farther away from one another due to the current rate of expansion, but a more aggressive dark energy would make this process unstoppable. The gravitational bonds that keep stars within galaxies could weaken. Picture it like a family gathering where everyone starts to slowly walk away from one another until they can no longer see each other. This separation would happen at an ever-increasing speed, until even individual star systems would start to unravel. Planets would drift away from their stars, unable to hold onto their orbits as dark energy pushes the space between them apart. Then, closer to home, the very structures that make life possible, molecules and atoms, could begin to disintegrate. If dark energy continues to intensify, it could pull apart not just the vast structures of the universe, but even the bonds that hold subatomic particles together. You'd be left with a universe that isn't just empty, but fundamentally broken, where the basic building blocks of matter no longer exist in any meaningful way. This is the rip in the big rip, the moment when space itself becomes too stretched for even the smallest things to hold together. The terrifying thing is that, unlike a slow decay, this process could happen quite suddenly on cosmic scales. Once dark energy reaches a certain point, the final unraveling of the universe could happen in a short period of time. If you were to witness it, you'd see everything accelerating away from you. Stars, planets, atoms, until all that remained was a cold, featureless void. But there's something hauntingly poetic about this, too. It speaks to the fragility of everything we take for granted. The laws of physics, the forces that bind us to the Earth, the stars in the night sky. All of it could be undone by a force that we can barely comprehend. The idea of a big rip feels distant, far off in the future, but it's a reminder that the universe is not eternal or static. It's evolving, and we are a small part of that story. The possibility of a big rip leaves us with questions about our place in this vast, ever-changing universe. It's not just a theoretical scenario, but a glimpse into the cosmic forces that dwarf our everyday understanding of time and existence. We think of the universe as stable, but there's something fundamentally unsettling about the idea that even space and time themselves could one day be torn apart, leaving nothing behind but a blank, empty canvas. When we think about the universe's beginning, we picture the Big Bang as the moment when everything exploded into existence from a single point. But the story isn't as simple as that. The Big Bang model, as powerful and as useful as it is, doesn't explain everything on its own. That's where dark matter and dark energy come in. They're not just afterthoughts or side characters in this cosmic tale. They seem to play critical roles in shaping what we see. But there's also a lingering sense that they might represent gaps in our understanding, hints that our grasp of the universe is still incomplete. From the very start, the Big Bang set in motion everything we know: space, time, energy, matter. But when physicists look at how galaxies behave and how the universe expands, they realize there's more going on than what can be accounted for by just the visible, familiar forms of matter and energy. Dark matter, for instance, is what's needed to explain how galaxies hold together. Without it, the universe doesn't add up. Galaxies should be flinging apart from each other, unable to stay intact given the amount of visible mass they contain. It's as though we're looking at a dance but can't hear the music. We know something unseen is orchestrating it, and that unseen force is what we've come to call dark matter. Dark energy complicates the picture further. The Big Bang wasn't just an explosion that sent things hurtling outward. That expansion is still happening, and it's speeding up. Dark energy is the name we've given to whatever's causing this acceleration, but it's a placeholder for something we still don't truly understand. It's like standing on a boat that's moving faster and faster, without knowing what's pulling you along or how to stop it. We need dark energy to explain what we're seeing, but it's a concept that could just as easily represent our ignorance, the fog over our eyes when it comes to understanding the deeper workings of the universe. In some ways, dark matter and dark energy are like pieces of a puzzle we've put into place without really knowing what the final picture looks like. They fit with what we observe: galaxies behaving the way they do, the universe expanding faster than expected, but we don't really know why they're there or how they work. This has led some to wonder: are they real, essential parts of the universe, or are they signs that our understanding of the laws of physics is incomplete? Maybe we're missing something fundamental about how gravity works on large scales, or perhaps the fabric of space and time itself behaves in ways we haven't yet figured out. It's possible that future discoveries will reshape our view entirely, revealing that dark matter and dark energy were just placeholders, shadows cast by something deeper we haven't discovered yet. But for now, they're the best explanations we have. They hold the universe together and drive its expansion, even if they remain invisible and mysterious. It's a bit like charting a map of an unknown land. You fill in what you can see, but there are always blank spots, areas marked with question marks. Dark matter and dark energy are those question marks. They tell us there's still much we don't know about how the universe works, leaving us both awed and humbled by the enormity of what remains hidden from our understanding. The idea of the multiverse is like standing at the edge of a vast ocean and realizing that, instead of just one horizon, there are infinite ones, each with its own mysterious shores. The Big Bang, our universe's fiery birth, paints a picture of a singular event, a colossal explosion that gave rise to everything we know, from the stars above us to the atoms in our bodies. But here's where things get strange, where the imagination stretches a little further than we'd expect. What if the Big Bang wasn't the only one? What if our universe is just one of countless others, each with its own Big Bang, its own beginning? The multiverse hypothesis suggests just that beyond the bubble of our universe, there could be an unimaginable number of other universes. Some might be eerily similar to ours, with galaxies, stars, and maybe even life forms that feel familiar. Others could be unrecognizable, governed by entirely different rules of physics, so alien to our experience that we wouldn't even know where to begin. The theory stems partly from the realization that the Big Bang could have been a local event, local on a cosmic scale, that is, picture an endless field of soap bubbles, each one a universe in its own right. Our Big Bang was the inflation of our particular bubble, but all around us, in directions we can't even point to, there could be other bubbles inflating and deflating. It's an unsettling thought, because as humans, we like the idea that we are the center of everything. We evolved in a world where the horizon seemed to mark the boundary of existence. First, we learned the Earth wasn't the center of the solar system. Then we learned the solar system wasn't the center of the galaxy. Now, the galaxy isn't even the center of the universe, and the universe itself might not be special. It's a bit of a blow to the ego, really. But the multiverse hypothesis doesn't just kick us down. It also offers a kind of comforting possibility. For every decision you've regretted, for every what-if moment, there could be a universe out there where things went differently. A universe where you took that job, called that person, or chose a different path. Not that it makes your decisions less meaningful here, but it's fascinating to think that in some distant corner of a multiverse, there might be a version of you living out that alternate reality. Then, there's the idea that some of these other universes might not just be out there in space, but could exist parallel to ours, just a dimension away, like the shadow of a hand that moves but never touches. Science fiction leans hard into these ideas because they appeal to our sense of wonder and fear. The fact is, no one really knows whether the multiverse exists or if it's just a byproduct of mathematical speculation, a tantalizing consequence of theories like inflation or string theory. The Big Bang certainly opened up these questions, suggesting that our universe had a beginning, and if ours had one, why not others? We are left staring out into the cosmic abyss, wondering if this is all there is or if we're just floating in one pocket of a grander, multiversal tapestry, waiting for the day when we might catch a glimpse of the others. And while the physics is complicated, the human reaction is quite simple: awe, excitement, and a hint of existential vertigo. Imagine, for a moment, that what we call the Big Bang was just one firework in an endless cosmic celebration, each explosion birthing a universe with its own story to tell. The idea that other universes could have had their own Big Bangs is rooted in a kind of cosmic democracy, where no one universe is the special one. Ours wasn't the first, it won't be the last, and it might not even be the biggest. Some universes may have burst into existence with as much drama and brilliance as ours did, while others may have been quieter, slower, or stranger in their beginnings. The concept here isn't just theoretical fancy. It actually comes from the implications of certain ideas in physics, like eternal inflation. Inflation theory, which explains the rapid expansion of our universe right after the Big Bang, suggests that while our universe expanded and cooled, other regions of space-time could have been doing the same, or something completely different. So, while we sit here, puzzling over our origin, other universes might have emerged, evolved, and even ended, their Big Bangs forgotten to anyone but themselves. It's funny to think about how attached we are to the idea that our universe is unique, when the science might be pointing in the opposite direction. It's kind of like growing up in a small town, convinced that you're living in the center of the world, only to realize there are countless towns, cities, and countries you've never even heard of. Other universes could have had their own Big Bangs that didn't just create different physics, but entirely different realities. Maybe in one of them, gravity doesn't behave the way it does here, or stars never formed, or perhaps life, if it exists at all, looks nothing like we could imagine. The thing that makes this idea so hard to grasp, though, is that we're trapped in our universe. We can't peek into these other places, if they exist, and so the idea of multiple Big Bangs remains tantalizingly out of reach, more of a philosophical possibility than something we can test or observe. But that doesn't make it any less real. There's something profoundly human in wondering about it. Our minds instinctively want to explore, to push past the limits of our understanding. And here we are, contemplating not just one universe but many, each with its own history of creation, its own violent birth into existence. In some ways, it's a humbling thought. Just as we've come to accept that our planet is one among many, that our galaxy is just another swirl of stars in a sea of others, we might also have to accept that our universe is one thread in a cosmic fabric too vast for us to fully comprehend. And these other universes, if they had their own big bangs, wouldn't care that we can't see them, just as the ocean doesn't care that we stand on the shore, trying to grasp its immensity. Imagine trying to play a game where each time you step onto a new field, the rules change. One moment, gravity pulls you down. The next, it pushes you up, or maybe sideways. This is what it might be like if the multiverse exists, and no, the laws of physics wouldn't necessarily be the same in each universe. In our universe, we've gotten used to things behaving a certain way. We rely on gravity, electromagnetism, the forces that bind atoms together. All these fundamental forces are part of the framework that makes everything tick. But the idea that every universe in the multiverse would follow the same rules? That's far from guaranteed. Some theories suggest that each universe could come with its own set of physical laws, like custom-tailored realities. Maybe in one universe, time moves backward or doesn't exist at all. In another, light might behave differently, or planets could form in ways we can't even fathom. It's not just about tweaking the familiar, changing a constant here or there. It's about a total reshuffling of how reality behaves. Some universes might have a recognizable structure where galaxies form, stars shine, and life, in some form, could emerge. But there could also be universes where everything is chaos, where matter can't even coalesce because the laws won't allow it. In a way, thinking about this gives us a sense of how precarious our own universe really is. Here, we have just the right balance of forces that allows atoms to form, planets to orbit stars, and life to evolve. The constants that make this all possible are, by cosmic standards, incredibly finely tuned. It's like the universe won the lottery in a multiverse where the odds were stacked against it. Other universes might not have been so lucky. Maybe they fizzled out moments after their own big bangs, or maybe they're still expanding, but without stars, without light, without anything that we would recognize as a universe at all. But here's where it gets interesting. If the laws of physics aren't the same everywhere, it changes how we understand everything. The things we take for granted, like cause and effect, the flow of time, the existence of matter, could be totally absent somewhere else. That's a mind-bender, for sure, because it forces us to accept that our universe's rules aren't universal. They're local, specific to our little bubble in the grand multiverse. The way a human might feel walking into an alien civilization, where nothing makes sense, is probably how we'd feel trying to make sense of another universe's physics. We tend to think of the laws of physics as unbreakable, as the ultimate rules of the game. But that's because we've only ever known one game. The multiverse, if it's real, opens the door to infinite games with infinite rules, many of which we couldn't begin to understand. And while that can be a little terrifying, because it means our understanding of reality is incredibly limited, it's also thrilling. It means that what we know might just be one version of a much larger truth, one that stretches far beyond what our minds can grasp. It's like discovering that every story you've ever heard is part of a series, and there are volumes upon volumes that have yet to be opened. Picture the Big Bang not as the creation of everything, but as a single spark in a much larger bonfire, one flare in a vast, cosmic landscape. The idea that the Big Bang could have been a local event within a much larger multiverse flips the way we usually think about the universe. We like to imagine the Big Bang as this singular, universe-defining moment, the ultimate origin story. But what if it was just one chapter in a much bigger, more complex book? This perspective suggests that the Big Bang might have been a local event, something that happened in one region of a much vaster reality or multiverse. Our universe, with its galaxies, black holes, and endless space, could be just a bubble, an expanding one, sure, but still just a small part of something larger. That larger multiverse might be filled with other bubbles, each one experiencing its own version of a Big Bang, or perhaps no bang at all. The idea of a local Big Bang comes from theories like eternal inflation, which suggests that while one part of space-time, our universe, was busy inflating and creating stars and galaxies, other parts of space-time could have been doing their own thing. Maybe they're expanding at different rates, or maybe they've already collapsed. Either way, the multiverse isn't one uniform space where everything follows the same timeline. Instead, it's a patchwork of universes, each doing its own thing, unaware of the others. We just happen to be in a part of this cosmic patchwork where our universe got its start with the Big Bang. Thinking of the Big Bang as a local event makes the universe feel a little less big in a strange way. Suddenly, everything we've ever known, our stars, our laws of physics, our entire cosmic history, is just a piece of a much larger reality that we can't even see. We're a neighborhood within a city, and the city itself is part of a sprawling, uncharted country. The sheer scale of it is mind-blowing, but it also makes sense in a weirdly intuitive way. Why should our universe be the be-all and end-all? In every other part of nature, there's never just one of anything. Stars aren't alone, galaxies cluster together, even the Earth is part of a solar system. So why should the universe itself be the exception, standing alone in a void? There's something oddly comforting about the idea that our universe isn't the whole story. It doesn't make us insignificant. Instead, it places us in a grander, more intricate framework. Sure, we might be just a small part of something bigger, but that doesn't take away from the uniqueness of our experience. Our Big Bang was still the birth of everything we know, but it's also possible that out there, far beyond the reaches of what we can observe, other universes are living out their own origins. They might not have a Big Bang at all, or maybe they had their own, completely different version of one. The local Big Bang theory suggests that while our universe feels all-encompassing, it might just be one event in a much larger, never-ending cycle of creations and destructions. The thought that there could be something beyond our universe doesn't diminish it. It just makes the cosmos feel even more layered and mysterious. We might never see or understand those other universes, but just knowing they could be out there makes our place in the multiverse all the more fascinating. Imagine you're standing at the edge of a vast, dark field, waiting for something to happen. In an instant, a tremendous flash lights up the entire landscape, and everything you can see starts rapidly expanding. That's a bit like how the early universe behaved, but much more extraordinary. The Big Bang Theory describes this moment when the universe first exploded into being, spreading out from an incomprehensibly hot, dense point. But this theory, by itself, left some unanswered questions. For instance, why does the universe look so uniform, so similar in every direction? And how did regions that are so far apart seem to have influenced each other? This is where cosmic inflation steps in, offering a kind of missing chapter in the early moments of the universe's story. Inflation theory proposes that, just a fraction of a second after the Big Bang, the universe went through an unimaginable burst of faster-than-light expansion. It didn't just grow. It grew so fast that things that were once microscopically small were suddenly spread across vast distances. You can imagine this like inflating a balloon, but doing so at such a dizzying speed that something as tiny as a speck of dust suddenly fills a room. The theory suggests that this brief moment of inflation lasted for only a billionth of a trillionth of a trillionth of a second, but during that time, the universe expanded exponentially. This rapid inflation helped smooth out any initial irregularities or variations, explaining why, billions of years later, when we look out into the cosmos, everything appears uniform in temperature and structure over large scales. If you think about the journey of the universe, it's almost like starting a marathon but suddenly sprinting the first 100 yards in an instant, covering so much ground so quickly that everything is spread out evenly. That's what inflation did. It also solved a few problems in the original Big Bang theory, like why distant regions of space are so similar in temperature, even though they shouldn't have had enough time to exchange heat or information. Inflation gives them that common origin, making it all fit together. Cosmic inflation also set the stage for the formation of galaxies and other cosmic structures. Though it smoothed things out on large scales, tiny quantum fluctuations that existed before inflation were stretched out, providing the seeds for the clumping of matter into galaxies and clusters over time. Those tiny ripples, born from randomness at a microscopic scale, expanded into the vast structures we see today. The beauty of inflation theory is that it turns the universe into something dynamic, constantly evolving and changing, rather than just a static bang. It's a story of transformation, where the early chaos of creation gave birth to the orderly cosmos we live in now, with stars, galaxies, and the possibility of life. It makes you wonder how something so rapid, so brief, could lay the foundation for everything we know today. It's a kind of cosmic race, hidden in the tiniest fraction of a second, but shaping the destiny of an entire universe. After the Big Bang, the universe didn't just settle into a calm, steady expansion. There was this brief but mind-bendingly intense moment where everything exploded outward faster than we can really comprehend. It's strange to think about how something so pivotal in shaping the entire universe could have happened in such an absurdly small amount of time. The period of rapid inflation, this wild burst of expansion, lasted for an incredibly short window, about 10 to the power of negative 32 seconds. That's such a tiny slice of time, it almost feels impossible to grasp. To put it into perspective, the blink of an eye takes about a third of a second. Now, if you imagine slicing that blink into trillions of pieces, inflation occurred in just one of those microscopic fragments. But in that microscopic fragment, the universe expanded exponentially, going from something subatomic in scale to something perhaps as large as a grapefruit or even larger, depending on how you visualize it. It's staggering to think that all the potential for stars, galaxies, and even life could have been packed into something so minuscule, and then, bam, it just ballooned out in an instant. What's fascinating about this is how it breaks our usual sense of time. We live in a world where things change gradually, where moments flow one after another in a predictable way. But during that brief flash of inflation, the rules of reality seemed different. Space itself stretched at an unimaginable rate, leaving everything it touched vastly far apart from everything else. And then, just as suddenly as it began, this rapid expansion stopped. The universe didn't pause, but the pace of its growth slowed down dramatically, settling into a more familiar rhythm of slower expansion that we're still seeing today. It's almost eerie when you think about how such a brief event could set the course for everything that came after. It's like a single breath that shaped the whole cosmos, a fleeting moment that determined the future of stars and planets, even life on Earth. And yet, we can't experience time the way the universe did in those moments. It's beyond our usual way of understanding, as if the early universe was in some kind of cosmic race, with inflation being that initial, blinding sprint that set everything in motion. Then it handed off the baton to the slower, steadier expansion we're more familiar with now. This brief moment of inflation is like the silent architect behind the universe we see today, a foundational event that came and went before we could even blink. It's hard to wrap your mind around what could cause something like inflation, this unimaginable, explosive expansion of the universe. But it all comes down to the strange and subtle rules that govern reality at its smallest scales. Before inflation kicked in, the universe was in a highly energetic, unstable state, something far more extreme than anything we're familiar with. Imagine the entire universe as a tightly coiled spring, crammed into a minuscule point, ready to release all its energy. This energy is what fueled inflation. The universe, in this state, was dominated by a form of energy that didn't behave like the matter or energy we deal with day to day. It was this weird, high-energy vacuum-like state, sometimes called a false vacuum. You can picture it almost as if the universe was stuck in an unnatural, pent-up tension, with this vacuum energy driving everything. At some point, this unstable energy tipped over, triggering inflation. The best analogy might be to think of it like water sitting at the top of a dam. It's quiet and still, but only because it's being held in place by the dam. Break the dam, and suddenly that water floods out in a rush, transforming everything downstream. Similarly, when the energy in that early universe was released, it unleashed inflation, rapidly expanding space itself in an almost chaotic rush. The universe expanded faster than the speed of light, but because space itself was growing, this didn't violate the rules of physics. But that unstable energy wasn't infinite. It wasn't meant to last. As inflation barreled forward, the universe began to cool, and that highly energetic state began to lose its grip. This is where things start to slow down. The energy driving inflation began to decay, like a fire running out of fuel. And just as suddenly as inflation had begun, it came to a halt. The universe transitioned out of that strange, high-energy phase into something more familiar, a lower energy state where particles, radiation, and the fundamental forces we know today could emerge. It's as though the universe had passed through this bizarre, violent phase of its early life and then, all at once, took a deep breath and slowed down, ready to let things take shape in a calmer, more ordered way. You could compare it to a balloon being blown up rapidly, only to stop at just the right moment before bursting, and then inflating more slowly, more steadily. What makes it so fascinating is the delicate balance. What caused inflation to start was this powerful, pent-up energy in the early universe, and what caused it to stop was the natural dissipation of that energy as the universe expanded and cooled. It's strange to think that the fate of everything, stars, galaxies, our planet, life, was shaped by that balance between the rush of inflation and the moment it stopped. In that tiny, fleeting transition, the universe settled into the pattern of expansion that's been unfolding ever since. When we look out into the universe, one of the most striking things is how smooth and uniform everything seems on the largest scales. No matter where you point a telescope, the universe looks roughly the same in all directions, with galaxies distributed in a similar way, and the cosmic microwave background, CMB, that faint glow left over from the Big Bang, showing a nearly identical temperature across the sky. It's a bit puzzling because you wouldn't expect such uniformity given the vast distances involved. Regions on opposite sides of the universe haven't had enough time to communicate or influence each other. So, how could everything look so coordinated? This is where the idea of inflation comes in like an elegant solution to a tricky problem. Before the inflationary period, the universe was incredibly small and dense. Everything was packed into such a tight space that different parts of it had plenty of time to interact and equalize their properties, like temperature. Think of it as sitting in a room with a heater on. Given enough time, the warmth spreads evenly throughout the room, so it's the same temperature everywhere. But then, inflation kicked in, and suddenly, that small, uniform room was stretched to a cosmic scale in the blink of an eye. All the parts of the universe that had once been in close contact were suddenly flung far apart from each other, still carrying that uniformity with them. This rapid stretching explains why distant regions of the universe, separated by billions of light years today, seem so similar. They were once right next to each other, sharing the same conditions before inflation expanded everything so dramatically. In essence, inflation froze in the smoothness of the universe by spreading it out over an enormous distance very quickly. Without inflation, we'd expect the universe to look much more chaotic, with some regions vastly different from others in temperature and structure. The uniformity of the cosmic microwave background, CMB, is one of the clearest pieces of evidence supporting this. The CMB is essentially a snapshot of the universe when it was just 380,000 years old, a time when it had cooled enough for light to travel freely through space. What's remarkable is how incredibly uniform this radiation is, with only tiny fluctuations in temperature on the order of 1 part in 100,000. Those tiny fluctuations represent slight differences in density, which later became the seeds for galaxy formation. But the overall smoothness of the CMB would be hard to explain without inflation. Inflation stretched the early universe so uniformly that when the CMB was released, it bore the imprint of that inflationary process, a nearly perfect smoothness with just the right amount of tiny variations for structure to form. So, yes, inflation is the key to understanding the uniformity we observe today. It allowed distant parts of the universe to share the same conditions in the past, and then spread them out across the vastness of space. Without this brief but intense period of expansion, the universe might have looked much more uneven, and we wouldn't have that nearly perfect backdrop of the CMB lighting up the early cosmos. Inflation, in that sense, didn't just shape the universe's structure. It made it coherent in a way that otherwise seems almost impossible. Quantum mechanics and the Big Bang Theory are two of the most profound ideas in modern science, and while they emerge from different areas, their intersection provides a fascinating glimpse into how the universe began. At its core, quantum mechanics deals with the behavior of particles on the smallest scale imaginable, at the level of atoms and subatomic particles. It's a world where things behave in strange, often counterintuitive ways, where particles can be in multiple places at once, and where they don't have definite positions until they are observed. For most of human history, these bizarre ideas would have been unimaginable, because we live in a world governed by classical physics, where objects move predictably and the laws of cause and effect seem to be solid. But quantum mechanics shattered that perception. Now imagine the moment of the Big Bang, about 8 billion years ago. Before this moment, the entire universe as we know it was compressed into a point smaller than an atom, a singularity. This was a realm where the laws of classical physics break down, and the only way to describe the conditions would be through quantum mechanics. In that incredibly dense, hot, and tiny state, particles were not only packed together, but their behavior was dominated by quantum uncertainty. The forces that control these subatomic particles, like the strong and weak nuclear forces, were crucial in shaping how the universe would expand. The human connection to this event comes when you think about the fact that everything you know, every star, every planet, and every human being, once existed in that singular point. There was no space, no time, just a potential for everything that would eventually become. It's difficult to wrap your mind around the idea that, in a sense, the particles that make up your body were subject to this chaotic quantum reality at the very start of the universe. What happened at that quantum level in the first split-second moments helped shape the entire universe's evolution. As the universe expanded and cooled, quantum mechanics still played a crucial role. In the very early stages, tiny quantum fluctuations, small variations in the density of matter, were stretched across the universe as space expanded. These quantum fluctuations are believed to be the seeds from which galaxies and stars eventually formed. It's strange to think that random blips of energy at the quantum level determined where the large structures of the universe would form billions of years later, but that's the case. People often think of the Big Bang as a huge explosion, but it was more like a rapid expansion from a very small, highly dense state. And in that expansion, quantum mechanics dictated the behavior of everything. The uncertainty principle, one of the cornerstones of quantum mechanics, meant that there were unpredictable shifts in energy and matter, shaping the universe into something far from smooth and uniform. These seemingly insignificant variations, brought about by the bizarre nature of quantum behavior, led to the formation of stars, galaxies, and ultimately, us. The intersection of quantum mechanics and the Big Bang can feel very abstract, but it's a reminder that the universe's most monumental moment was built on the tiniest building blocks, behaving in ways we still struggle to fully comprehend. And in the heart of that is a human story. We are all made of stardust, forged from the quantum world. It's humbling to realize that the laws of nature, which seem so foreign when we look at the quantum world, played such an intimate role in the creation of everything we hold dear today. Understanding how the universe started is not just a scientific quest. It's a journey into our own origins. What governed the very first moments of existence, the rules that dictated how the universe would evolve, also dictated that human beings could eventually come into existence, look up at the stars, and wonder how it all began. The idea that quantum fluctuations could have sparked the emergence of the universe from nothing is one of the most intriguing and challenging concepts in cosmology. It strikes at the core of the biggest question humanity has ever asked. Why is there something rather than nothing? To grapple with this, we first have to rethink what nothing means, especially in the context of quantum mechanics. In our everyday lives, nothing seems like an absolute absence. No space, no matter, no time. But in the quantum world, even what we might think of as empty space isn't truly empty. Instead, it's a seething, fluctuating environment filled with potential. Particles can pop in and out of existence due to quantum fluctuations. These aren't particles in the way we think of a ball or a chair. They are tiny bursts of energy that flicker into being, only to vanish again almost instantly. This is possible because, at the quantum level, energy and time have a curious relationship. The shorter the time, the greater the amount of uncertainty about what energy can do, meaning that for brief moments, particles can come into existence even if they seem to borrow energy from nowhere. Now, imagine applying this bizarre, counterintuitive principle to the universe itself. Could it be that the universe itself came from one of these quantum fluctuations? Some physicists argue that the universe might have emerged spontaneously from this kind of quantum nothingness, where what we call nothing still holds the potential for something. When we talk about the universe arising from nothing, it's not that it popped out of a pure void. Rather, even nothing is something in the quantum world. The vacuum isn't a blank slate, but a dynamic space full of possibilities. And it's in that potential-filled emptiness where something as grand as a universe might take shape. What's astonishing here is the thought that, at the most fundamental level, the universe's existence could be the result of a random, unpredictable fluctuation, an event governed by chance rather than purpose. It's unsettling because it challenges our human desire for things to have reasons, for existence to have a clear cause. The possibility that everything, from galaxies to human consciousness, might owe its existence to a spontaneous, quantum blip pushes us to the limits of what we can emotionally process. There's a certain discomfort in thinking that randomness, something we usually try to avoid, could lie at the heart of everything. But there's also something poetic about it. Imagine that the universe, everything you see and know, the stars, the people you love, might have emerged from one of these small, fleeting fluctuations. It feels like a kind of cosmic lottery, one in which we all somehow won. The delicate balance of forces, the expansion of space, and the rise of complexity. Everything was set in motion by what could have been a momentary event in an ocean of quantum uncertainty. On a personal level, this idea forces us to reflect on how we view our existence. If quantum fluctuations could have produced a universe from nothing, it reframes the way we think about beginnings and causes. We want there to be a grand reason for everything, something concrete we can point to, but what if there isn't? What if the reason we exist is simply that in a quantum world, strange things happen, and we just happen to be the result of one of those things? It's a stark reminder of how vast and mysterious the universe is and how our understanding of existence is constantly evolving. For a human being, it might feel isolating at first. The notion that the universe could be a byproduct of randomness, with no grand design or purpose. But it can also be a source of wonder. If quantum fluctuations can create something as vast and complex as the universe from what appears to be nothing, then the potential for creation, for existence, for beauty is far greater than we ever imagined. We are all part of that incredible, improbable fluctuation, a cosmic ripple that gave rise to stars, planets, life, and eventually, us. And in that randomness, there's something profoundly human, a reminder that life itself, against the odds, persists and flourishes. In the very early universe, quantum effects weren't just a side detail, they were central to everything. At that time, when the universe was smaller than an atom and unimaginably hot, the familiar rules of classical physics simply didn't apply. Space and time themselves were in such an extreme state that only quantum mechanics could describe what was happening. The universe was in a realm where particles and energy fluctuated in a chaotic, uncertain way, and this uncertainty played a vital role in shaping the cosmos as we know it. It's strange to think about, but in those first fractions of a second, the universe was governed by randomness and unpredictability at a microscopic level. Quantum effects meant that particles didn't behave according to the neat, orderly rules we're used to. They appeared and disappeared, entangled with one another in ways that defy everyday experience. And yet, out of this unpredictability emerged the seeds for everything we see around us today. The ripples and variations that occurred due to quantum effects during these moments laid the groundwork for the formation of galaxies, stars, and planets. It's like thinking of the early universe as a sea of energy, roiling and turbulent, with particles dancing in and out of existence. These quantum fluctuations, tiny as they were, had enormous consequences as the universe expanded and cooled. They weren't just insignificant blips, they were crucial because the small differences in energy density caused by these fluctuations became the scaffolding for all the large structures that formed later. Every galaxy that exists today traces its origins to these early quantum effects, which determined where matter would clump together as the universe evolved. When you look up at the night sky and see the stars scattered across vast distances, it's mind-boggling to realize that those patterns, those structures, can be traced back to quantum effects in the first tiny moments of the universe's life. Those early quantum variations might have been random, but their impact was profound. Without them, the universe might have remained a featureless, uniform expanse, a far cry from the richly diverse cosmos we inhabit. The randomness and uncertainty of quantum mechanics are, in a way, responsible for the existence of everything. This adds a deeply human element to the story of the universe. The idea that our existence is connected to these strange, invisible quantum effects makes you feel like you're part of something much larger and much more mysterious. In a sense, we are all the product of randomness and uncertainty, and yet here we are, capable of asking questions, seeking meaning, and understanding the universe. It's a paradox that something so unpredictable could give rise to the complexity and order we experience today. But that's what quantum mechanics teaches us. Out of uncertainty, beauty and life can emerge. The early universe reminds us that, even in chaos, there is potential. The same randomness that governed particles in those first moments also set the stage for a universe capable of supporting life. It's not just a scientific idea. It's a reminder of how interconnected we are with the fabric of reality, even at its most fundamental, quantum level. In that tiny, hot, quantum-dominated universe, the seeds of everything were sown, including the possibility for us to exist and wonder about where it all came from. Scientists have been wrestling with the challenge of reconciling general relativity and quantum mechanics for nearly a century because these two pillars of modern physics describe reality in profoundly different ways. General relativity, Einstein's masterpiece, is our best tool for understanding the universe at large scales. It describes how gravity works, not as a force pulling objects together, but as the bending and warping of space and time caused by mass and energy. This theory beautifully explains the motion of planets, the bending of light around stars, and even the behavior of black holes. It's how we understand the universe's expansion since the Big Bang, how galaxies move, and how massive objects interact on a grand scale. Quantum mechanics, on the other hand, focuses on the smallest scales, particles, atoms, and the forces that govern their interactions. In this realm, the smooth, predictable space-time fabric that general relativity depends on doesn't exist in the same way. Quantum mechanics deals with uncertainty, probabilities, and strange effects like entanglement, where particles can affect each other instantaneously across vast distances. The two theories seem to be speaking entirely different languages, describing different realities. Yet, the universe isn't neatly divided into the large and the small. When you start thinking about extreme conditions, like what happened at the moment of the Big Bang or inside black holes, where gravity is incredibly strong and the scales are minuscule, both general relativity and quantum mechanics should apply. But they don't fit together seamlessly. General relativity treats space and time as continuous, smooth fields, while quantum mechanics describes the world in terms of discrete, tiny packets of energy. It's like trying to combine a calm ocean with a violent storm and make them work together under the same set of rules. This mismatch has driven physicists to search for a unified theory, often called quantum gravity, that would combine the two. The goal is to develop a framework that works at all scales, from the subatomic to the cosmic. One of the most well-known attempts is string theory, which suggests that particles aren't really points, but rather tiny vibrating strings, and that these strings exist in more dimensions than we can perceive. By adding these extra dimensions, string theory aims to bridge the gap between quantum mechanics and general relativity, smoothing out the conflicts between them. Another approach, called loop quantum gravity, takes a different path by trying to quantize space and time themselves, suggesting that space and time come in discrete chunks, much like how matter is made of atoms. This theory tries to directly apply quantum principles to gravity without needing extra dimensions, offering another potential route to reconciliation. For scientists, this struggle isn't just a dry, technical problem. It's a profound quest to understand the deepest nature of reality. The conflict between general relativity and quantum mechanics forces us to confront our limits, to accept that the universe may work in ways that are far beyond our current understanding. The human element in this story comes from the passion and drive to find answers, even when they seem elusive. Physicists are trying to look into the very heart of existence itself, to understand the underlying structure of everything, from the way galaxies move to the behavior of particles at the smallest scales. And even though the answer remains out of reach, each step toward reconciling these two great theories is a step closer to unlocking the universe's most hidden secrets. The difficulty in bringing these two frameworks together reminds us of the complexity of the universe and how much we still have to learn. But it also highlights the tenacity of the human spirit, the drive to push beyond what we know, to seek deeper understanding, even when the pieces don't quite fit yet. It's a journey toward a more complete picture of reality, one that might not just reveal the origins of the universe, but offer insight into its ultimate nature and our place within it. The future of the universe is a question that tugs at our natural curiosity. We look up at the stars and wonder where it all leads. Science tells us that the universe is expanding, and it has been since the Big Bang. But where this expansion takes us has long been a matter of debate. Will the universe keep spreading out, growing colder and emptier until it is a vast, silent void? Or will it slow down, reversing course in a dramatic collapse, ending in what's been dubbed the Big Crunch? To imagine the universe expanding forever is to picture a place where everything we know is growing more distant. Galaxies are speeding away from each other, the space between them stretching out like a rubber band being pulled in every direction. But it's more than just distance. The fabric of the universe itself is getting thinner. Stars burn out, galaxies drift apart, and over unimaginable timescales, even the atoms that make up everything could begin to disintegrate. We'd be left with nothing but cold, lifeless remnants scattered across an impossibly vast, dark cosmos. This future, sometimes referred to as heat death, is not violent or dramatic. It's slow, creeping, a long fade into stillness. On the other hand, the idea of a big crunch offers a very different fate. Imagine if the universe's expansion began to slow down, like a ball thrown into the air, reaching its peak before gravity pulls it back. If there's enough matter in the universe, if the gravitational pull between galaxies is strong enough, then one day the expansion could stop. Slowly at first, everything would start moving inward, pulled by gravity. Galaxies would begin to collide, stars crashing into each other in cataclysmic explosions. The universe would become hotter, denser, and more chaotic as everything collapsed into a fiery, singular point, not unlike how it all began. This scenario is far more violent, filled with cosmic destruction before everything is consumed. Right now, the evidence seems to lean towards the first scenario. Observations of distant galaxies suggest the universe's expansion isn't slowing down. It's speeding up, driven by a mysterious force we call dark energy. Dark energy makes up about 68% of the universe and works against gravity, pushing everything apart. With this discovery, the idea of a big crunch has become less likely. It seems more probable that we are heading for an ever-expanding universe, one that will grow colder and darker over time. What does that mean for us? On a human level, it's hard to relate to timescales that stretch beyond trillions of years. Our existence is just a blink in the cosmic timeline. But thinking about the universe's fate is also a reminder of how fleeting and precious life is. Whether the end comes in fire or ice, it's far, far in the future. The stars we see today, the galaxies we study, they will change, but we won't be around to witness it. In the end, it's not about fearing the universe's end, but appreciating the here and now, our brief, bright moment in a universe that is always changing. The universe, as vast and mysterious as it is, may be slowly heading towards a fate that is far from the fiery end many might imagine. Instead, it could simply freeze. The Big Freeze, as it's often called, paints a picture of a cosmos that just keeps expanding, but at a terrible cost. As galaxies drift further and further apart, space itself stretches like an unending breath, leaving everything more isolated. The result isn't violent, but quietly devastating. Over billions and trillions of years, the stars that fill our night sky will burn out one by one, exhausting the fuel that keeps them alive. New stars, once born from the cosmic dust of old ones, will stop forming. The galaxies, now lonely and dark, will continue to float away from each other in a universe that becomes increasingly empty. The temperature of the universe will gradually fall. As space expands, it cools, like air spreading in all directions. Right now, there's still some warmth left from the Big Bang, a faint glow called the cosmic microwave background radiation, but even that will eventually fade into near absolute zero, where energy itself becomes scarce. In this cold, desolate future, no new light will be made. It's a universe that just keeps growing colder, dimmer, and more isolated. The elements that once came together to form everything, stars, planets, life itself, will either drift apart or be locked inside dead stars and black holes. But there's something deeply haunting about the idea that this isn't an abrupt end, like a crash or explosion, but a slow, creeping stillness. Time stretches out infinitely, but without the warmth of stars or the activity of galaxies, it will seem like a frozen, silent place. No sound, no light, just space, expanding endlessly. And as the last black holes evaporate into faint radiation over a staggering amount of time, even those final traces of structure will vanish. The universe will be left as an almost featureless, empty expanse. On a human level, it's the eeriness of this scenario that hits hardest. It's not the chaos of destruction that frightens us, but the stillness of it. Life thrives on activity, on change, on warmth. The thought of an existence without any of those things seems almost unbearable. In a way, it mirrors our own fears of being forgotten, of growing distant, of a quiet, lonely end. The Big Freeze is a reminder that while we may fight against time, trying to leave our mark in the universe, there may come a point where even the universe itself loses all memory, all trace of what once was. And yet, knowing that such an end is so far beyond our reach gives us permission to marvel at the stars we can still see, to cherish the warmth of a universe that, for now, still has life and light left in it. Dark energy is the force that most of us will never feel directly, yet it plays a profound role in shaping the ultimate destiny of the universe. It's invisible, mysterious, and makes up nearly 70% of the universe's energy. And despite our everyday experience, where gravity pulls things together, dark energy does the opposite. It pushes the universe apart. This quiet, relentless force is what's causing the universe's expansion to accelerate, and the implications of that are enormous. At first, scientists thought that the expansion of the universe, set in motion by the Big Bang, would eventually slow down. Gravity, the force that draws things together, was expected to pull everything back in, or at least keep the expansion in check. But when we look at distant galaxies today, what we see is surprising. They're not just moving away from us, but they're speeding up. That's where dark energy comes in. It's not just stretching the fabric of space-time. It's doing it faster and faster, like an invisible hand pulling the universe in all directions at once. And if it continues doing that, the universe is in for a strange and solitary future. In the long term, dark energy will drive galaxies so far apart that their light will no longer reach one another. Future astronomers, if they exist, would look up at the night sky and see nothing but emptiness. The stars, the galaxies, everything that makes up the grand cosmic tapestry will become unreachable. Each galaxy will be like an isolated island in an ever-growing ocean of space, with no way of ever communicating with or seeing any other galaxy again. It's a deeply unsettling thought. A universe not just cold and dark, but lonely beyond imagination. But dark energy's influence doesn't stop there. The more it pushes, the more it dominates. If this expansion keeps accelerating, dark energy could ultimately pull apart not just galaxies, but stars, planets, and even atoms. In this extreme scenario, known as the Big Rip, the force of dark energy could become so strong that it overwhelms all the other forces in nature. Galaxies would be torn apart, then solar systems, then planets, and finally the atoms themselves would disintegrate into a sea of particles. It would be the ultimate undoing of everything, not in fire or ice, but in a slow and methodical tearing apart of the very fabric of existence. It's hard to wrap our minds around dark energy because it's so unlike anything we experience. We understand gravity, we feel it every day, but dark energy is something entirely different. And yet, it's determining the ultimate fate of everything. On a human level, it feels like confronting something inevitable but deeply strange, a force that shapes our destiny without us ever noticing it in our daily lives. In the end, dark energy reminds us that the universe is much stranger and more complex than we can ever fully grasp, and that we are just passengers in a cosmos driven by forces far beyond our control. The idea of a big bounce offers a universe that doesn't simply end, but instead keeps cycling through periods of death and rebirth. It's a vision that counters the finality of a big crunch or a big freeze, and instead suggests something more rhythmic, like the universe breathing in and out over immense stretches of time. Imagine if, after expanding for billions of years, the universe started to contract again. Galaxies would begin moving toward each other, eventually leading to a massive collapse. But rather than ending in a singular, final destruction, this collapse could trigger a new beginning, another Big Bang, and with it, the birth of a new universe. For those who think about the universe in human terms, this idea feels strangely hopeful. We know that life, our lives, are full of cycles: birth, growth, decay. And the universe, in this scenario, wouldn't be any different. It wouldn't just expand infinitely into a cold, distant void or collapse into a final fiery end. Instead, it would constantly renew itself. The thought of everything ending is unsettling. The idea that after all the stars have burned out and galaxies have collided, there's the potential for another universe to form, perhaps with new stars, new galaxies, even new forms of life, gives this cosmic story a sense of continuity. The Big Bounce idea comes from a different way of thinking about gravity and space-time. If space and time are fluid and not fixed, maybe they can bend, stretch, and contract like elastic. In this scenario, after reaching a maximum size, the universe's expansion would slow down, halt, and reverse. The entire cosmos would shrink back down, not into a singularity like we imagine with the Big Crunch, but perhaps into something more manageable, ready to explode out again. It's an endlessly repeating cycle, a universe that never truly begins or ends, but simply goes through phases. For some physicists, this idea solves a troubling question about the original Big Bang. Where did it come from? If the universe has gone through many bounces, then maybe it didn't need to come from nothing. Each expansion could be the result of the last contraction, and this could have been happening forever. Time itself becomes cyclical, and our universe could just be one of countless others that came before it. This is hard for us to comprehend because we're used to thinking in terms of beginnings and endings, but in a big bounce model, those concepts get blurry. For us, living in such a universe would mean that while we experience time moving in one direction, the larger picture would reveal a kind of cosmic heartbeat. The universe's cycles are so long that we'd never witness more than one. But the idea that the cosmos isn't a one-time event but an ongoing process makes everything feel less final. The future might not be about surviving or escaping a cold, dark end, but instead about understanding that the universe, much like life itself, is always in motion, growing, shrinking, and starting anew, far beyond the limits of human time and perception. The Big Bang Theory is the starting point for almost everything we know about the universe, but it does more than just explain how things began. It gives us a framework for thinking about where everything might be headed. The idea that the universe started as an incredibly hot, dense point and then rapidly expanded sets the stage for understanding the universe as something dynamic, constantly in motion. From the moment of that initial explosion, the universe hasn't stopped evolving, and its expansion is the key to figuring out its future. When we think about the Big Bang, it's not just a single event frozen in the past. It's something that echoes through time, shaping how galaxies form, how stars burn, and how the fabric of space itself behaves. The energy that was released in that first moment still pulses through the universe as cosmic microwave background radiation, a faint afterglow that reminds us of that explosive beginning. But it's the expansion that matters most for predicting the long-term fate of everything. The fact that the universe is still stretching outward tells us that it's not a stable, unchanging place. Instead, it's in a constant state of flux, which means it's always moving towards some eventual outcome. The rate of this expansion, first measured by Edwin Hubble, showed that galaxies are moving away from each other, which was the first clue that the universe isn't static. But in the decades since, scientists have realized that this expansion isn't slowing down as they once thought. It's speeding up, driven by something we call dark energy. This discovery changed everything. If the universe is expanding faster and faster, it suggests that a collapse, like the one that could lead to a big crunch, is less likely. Instead, the Big Bang has set the universe on a path where it might continue expanding indefinitely. The Big Bang Theory also makes us aware of the limits of time. The universe had a beginning, so it's reasonable to think that it could also have an end. But what that end looks like depends on how the forces at play interact over unimaginable timescales. If dark energy continues to dominate, then we might be looking at a future where the universe expands so much that it becomes cold, dark, and empty, what's often called a big freeze. The Big Bang's expansion won't stop, but rather carry everything so far apart that galaxies, stars, and even atoms eventually fade into nothingness. However, the Big Bang also hints at other possibilities. Some theories, inspired by the Big Bang's mechanics, suggest that the universe could one day reverse its expansion, leading to a contraction and perhaps a rebirth in the form of another Big Bang. This cyclical universe idea, where the Big Bang is just one phase in an endless series of expansions and contractions, offers a vision of a universe that doesn't die, but continually renews itself. Ultimately, the Big Bang Theory tells us that the universe is dynamic and always changing. It forces us to think about the universe as something that began and, like everything else, might end in one form or another. Whether it expands into an eternal freeze, collapses into a singular point, or cycles through endless phases, the Big Bang is the key that unlocks the story of the universe's beginning and hints at its future, even if that future stretches beyond anything we'll ever witness. Understanding the Big Bang is understanding the universe's potential fate, reminding us that everything, no matter how vast, has a journey. The Big Bang Theory has long been the leading explanation for the origin of the universe, but it's not the only one. While the idea that everything began from a singular, explosive event has captured the imagination, it's not a theory without its challenges. There are alternatives that paint a different picture of the cosmos, and they've been proposed by scientists who saw gaps in the Big Bang narrative or sought to explain phenomena it couldn't fully account for. One of the earlier alternatives is the steady-state theory. This idea was proposed in the mid-20th century as a challenge to the concept of a finite beginning. Its proponents argued that the universe has no beginning or end. Instead, it remains essentially the same throughout eternity. To balance the expansion of space, new matter would need to be continuously created. This would keep the universe looking the same on large scales over time, never changing in its overall appearance. The appeal of the steady-state model was that it avoided the unsettling notion of a sudden creation event. It gave the universe a timeless quality, always existing, always expanding, and yet always maintaining a consistent structure. But over time, the evidence began to pile up against it. Observations like the cosmic microwave background radiation, remnants of the Big Bang, and the fact that galaxies seem to be evolving over time forced the steady-state theory into the shadows. Still, there's something quite human in the desire for the universe to be eternal, always present, as if the cosmos itself mirrors our instinct to search for permanence in an ever-changing world. Then there's the ekpyrotic universe, a much more recent and perhaps more radical departure from the Big Bang. Imagine that the universe isn't a one-time event, but part of an endless cycle of creation and destruction. In this model, the universe begins not with a bang but with a collision, two vast, higher-dimensional brains, a concept borrowed from string theory, smashing into each other. Instead of a singular, explosive moment of creation, the universe is born from the energy released in this collision. Time, in this scenario, is cyclical. The universe expands, then eventually contracts again, leading to another collision that sparks a new universe. It's a cosmic reset, over and over again. There's something profound in this idea. The universe is no longer a linear narrative, but a story that loops endlessly, like the natural cycles we see all around us on Earth. Birth, death, rebirth, a reflection of the cycles of human life, mirrored on a scale almost too vast to comprehend. But neither of these alternatives are without their own hurdles. The steady-state theory struggled to explain certain observations, and the ekpyrotic model is rooted in theoretical physics that's far from being conclusively proven. Still, they both reveal something fascinating about how people approach the unknown. In science, just as in life, we search for patterns, for explanations that make sense of the chaos around us. We build models of the universe that reflect our own hopes, fears, and instincts. The Big Bang is a story of creation from nothing, a grand narrative that speaks to a universe with a beginning, much like how humans experience life with a start and an end. The steady state speaks to our yearning for continuity, while the ekpyrotic model embodies the hope for cycles, for renewal, for second chances. Each theory, whether it's ultimately proven or not, tells us as much about ourselves as it does about the cosmos. There's something unsettling about the idea of the universe having a clear beginning, and maybe that's why people have been picking apart the Big Bang theory for decades. It's not that the theory is wrong, at least not in the broad strokes. The evidence for an expanding universe, the discovery of cosmic microwave background radiation, those things fit too perfectly to dismiss. But the Big Bang doesn't explain everything, and some of the gaps in the theory feel like those unsolved parts of life that nag at the back of your mind, never fully resolved. One of the biggest issues is the idea of singularity, the moment when everything in the universe is supposed to have been packed into a single, infinitely dense point. It's a beautiful and terrifying concept, but it doesn't play well with the laws of physics as we know them. When you try to merge general relativity, which describes gravity, with quantum mechanics, which governs the smallest particles, things fall apart. Our equations don't make sense at that level, as if the universe is laughing at us, daring us to figure out how these two theories could ever live together in harmony. It's like two people who should, in theory, get along but just don't, no matter how hard you try to reconcile their differences. This leaves us with a puzzle. We can describe what happened right after the Big Bang, but we have no clear idea of what happened in the very first moment, or what caused it to happen in the first place. Then there's dark matter and dark energy, which feel like ghosts haunting the universe. The Big Bang doesn't account for them, and yet, they seem to make up most of what's out there. We can't see dark matter, but we know it's there because galaxies spin faster than they should. Something is holding them together, something invisible but undeniable. And dark energy? It's even stranger. It's the force driving the universe to expand faster and faster, as if space itself is being stretched, but we have no real grasp of what it is. The Big Bang Theory has no explanation for either of these invisible forces, leaving us fumbling in the dark, trying to make sense of a cosmos that doesn't behave the way we expect it to. There's also the horizon problem, which speaks to how eerily uniform the universe is. When we look out at the farthest reaches of space, the temperature of the cosmic microwave background radiation is almost exactly the same everywhere. The problem is, the universe hasn't been around long enough for all those distant regions to have communicated with each other and reached this kind of equilibrium. It's like walking into a room full of strangers who've somehow all agreed on the same story before you got there, even though they shouldn't have had the time or means to compare notes. Inflation, a rapid expansion of space just after the Big Bang, is supposed to explain this, but even inflation raises more questions than it answers. Why did it happen? What triggered it? And did it ever stop? It's as if every solution comes with its own set of problems. Even the Big Bang's timeline can feel counterintuitive. When scientists talk about the first few seconds of the universe, they're describing an environment so alien that it's hard to even imagine. Particles colliding, forces splitting apart, temperatures that make the center of the sun look like a mild summer day. But how did those first particles even come into existence? And how did they know what to do? The Big Bang gives us a framework, but the details of how a simple burst of energy turned into galaxies, stars, and life remain fuzzy at best. It's like trying to map out your life story starting from a single moment of birth, while all the richness and complexity of what comes after feel like a mystery. So, while the Big Bang Theory has given us an incredible narrative of the universe's origin, it leaves us with profound, nagging questions. There's still so much we don't know, and maybe that's part of what makes the whole thing feel so human. The gaps, the unknowns, the mysteries that we keep poking at, hoping to understand. We've figured out a lot, but the universe still holds its secrets close, making sure we never get too comfortable with the answers we think we have. Imagine for a moment that everything we think we know about the universe could be upended with just one key observation, a single piece of evidence that doesn't fit into the picture we've carefully constructed. The Big Bang Theory, while powerful, is still a model, an explanation based on what we've seen so far. But models can be broken, and the idea that the universe began with a singular explosive event could be overturned if we stumble upon the right, or rather the wrong, kind of evidence. For example, if we were to discover that the cosmic microwave background radiation, the supposed afterglow of the Big Bang, wasn't as uniform as it appears, that could shake the foundations of the theory. Right now, we see this radiation as nearly smooth, with just tiny fluctuations. These fluctuations match the theory's predictions, showing how early clumps of matter eventually formed galaxies. But what if we found larger, unexplained anomalies or patterns in this radiation? If the cosmic background revealed structures that couldn't have possibly formed from the rapid inflation of the universe right after the Big Bang, it would be like finding a glitch in the Matrix. That would suggest we've misunderstood something fundamental about the universe's origin, or that there's some deeper mechanism at play that the Big Bang alone can't explain. Or imagine looking out into the farthest reaches of space and seeing galaxies that shouldn't be there. The Big Bang Theory predicts a timeline. Galaxies and stars should only appear after a certain period of cosmic evolution. But what if, using more advanced telescopes, we found galaxies much older than they should be? If we found mature, well-formed galaxies in regions of space where the universe should still be in its infancy, the entire timeline would come under scrutiny. It would be like discovering ancient ruins in a city that's only a few decades old. It wouldn't make sense, and it would force us to rethink the entire history of the universe. We'd be left wondering if the Big Bang, as we know it, is just one chapter in a much longer cosmic story that we've only begun to understand. Another scenario involves dark matter and dark energy, those mysterious forces that make up most of the universe but remain largely invisible to us. If we were to discover evidence that dark energy doesn't behave as the Big Bang model suggests, or worse, if dark matter turns out to be something completely unexpected, our current understanding could unravel. The Big Bang Theory doesn't really explain why the universe is expanding at an accelerating rate due to dark energy. If we find out that dark energy isn't just some uniform force but something dynamic, changing over time, we might need to scrap our current picture of how the universe began and evolved. The discovery of these forces behaving in ways that contradict the Big Bang model would be akin to suddenly finding out that gravity sometimes repels rather than attracts. It would be a complete paradigm shift. Then there's the question of what might lie beyond our observable universe. We can only see a fraction of the cosmos, the part of it whose light has had time to reach us. If we could peer beyond that boundary and found a universe that looks wildly different, perhaps one that isn't expanding at all, or even one filled with entirely different laws of physics, that would force a complete reconsideration of the Big Bang. It would suggest that our universe is just one piece of a much larger, more complex reality, and the Big Bang might only explain what happened here, locally, rather than universally. In science, we're always standing on the edge of the unknown. The Big Bang Theory is our best guess right now, a model that fits most of what we've observed. But one unexpected piece of evidence could send us back to the drawing board, forcing us to confront the uncomfortable possibility that we don't understand the universe as well as we thought. It's like building a puzzle and you're almost done, but then you find a piece that doesn't fit anywhere. Was the puzzle incomplete all along? Or are we missing a whole other layer of the picture we've been trying to put together? The universe, vast and mysterious, always seems to have the last laugh, keeping its secrets just out of reach. The universe is a tricky place, and sometimes it doesn't seem to play by the rules we set for it. One of the puzzles that has caught people off guard is how quickly galaxies seem to form after the Big Bang. When we look at some of the farthest, and therefore oldest, galaxies, they appear far more developed than they should be. According to the timeline of the Big Bang, these galaxies shouldn't be as large, as structured, or as rich with stars as they are, given the limited time they've had to evolve. It's like walking into a bakery first thing in the morning and finding shelves filled with fresh bread, even though the ovens haven't been on long enough to bake them. The Big Bang Theory doesn't ignore this issue, though. One way it explains this rapid galaxy formation is through the concept of inflation, a rapid, almost unimaginably fast expansion of the universe that happened in its first fraction of a second. Inflation stretched the universe from something smaller than an atom to a massive expanse in an instant. This process didn't just spread matter out. It smoothed out irregularities and gave the cosmos a kind of head start. During inflation, tiny quantum fluctuations, little wiggles in the fabric of space, were stretched to cosmic scales. These fluctuations became the seeds of everything we see today. So when the universe finally slowed down and cooled enough for matter to start clumping together, there were already blueprints in place for galaxies, stars, and clusters to form. These primordial seeds created pockets of higher density where matter gathered more quickly, allowing galaxies to appear sooner than we might have otherwise expected. Another key part of the explanation comes from the role of dark matter. Dark matter is invisible, but its gravitational pull is very real, and it's believed to make up most of the matter in the universe. Right after the Big Bang, dark matter played a crucial role in helping galaxies form faster than normal matter could on its own. It doesn't interact with light or radiation like normal matter does, so while regular matter was still tied up in hot plasma, unable to cool and form structures, dark matter was already starting to clump together. These dark matter clumps acted like scaffolding, pulling regular matter toward them and helping galaxies take shape faster than they would have through the gravitational effects of normal matter alone. It's like building a house more quickly because the frame is already in place before the walls and roof go up. But even with inflation and dark matter, there's still a bit of a mystery. Observations of galaxies forming earlier and faster than expected challenge our models of how galaxies evolve. It's as if we're watching a movie and some scenes are playing out faster than the plot seems to allow. Scientists are constantly refining the details, adding layers of complexity to the Big Bang model to account for these observations. For instance, interactions between galaxies, like mergers, where smaller galaxies combine to form larger ones, may have sped up the growth process. These early galaxies, caught in a cosmic dance of collision and fusion, could have grown far more rapidly than we once thought possible. In some ways, this rapid galaxy formation reminds us that the universe is full of surprises. Even with the best models, we're often left playing catch-up with new data, scrambling to understand why the cosmos doesn't always unfold at the pace we predict. But that's the human side of science, always revising, questioning, and learning, as the universe continues to reveal itself in ways that are both familiar and entirely unexpected. Just when we think we've figured out the rules, the universe shows us that it's a little more complicated, a little faster, and a lot more fascinating than we imagined. Imagine standing on a quiet hillside at night, looking up at the sky, filled with countless stars, wondering how it all began. The journey to understanding the origin of the universe starts in moments like these, moments of awe and curiosity. People like Edwin Hubble had similar thoughts, and he took those questions and pointed a telescope into the night sky, finding something incredible. He noticed that the light from distant galaxies wasn't just sitting still. It was stretched out, becoming redder as it traveled through space. This was the first clue. Galaxies were moving away from us, and the universe itself was expanding. It's a bit like seeing a firework from far away. The farther you are, the more it seems to move outward. This redshift in the light told us that the universe wasn't static. It was like a rubber band stretched tight, a place that had started in a dense, hot state and then expanded over time. But that's not where the story ends. Back in the 1960s, two scientists, Arno Penzias and Robert Wilson, found something they didn't expect. They built a radio antenna and were trying to get clean signals, but there was this persistent hiss, a faint noise that seemed to come from every direction in the sky. It wasn't just random interference. It was more like the faint, lingering heat of an extinguished bonfire, except, in this case, the bonfire was the Big Bang itself. This noise turned out to be the cosmic microwave background radiation, a remnant heat that had been traveling for over 13 billion years. It was a whisper from the universe's infancy, still echoing through space. That background radiation told a story of a universe that was once incredibly hot and dense, then cooled as it expanded. And then, there's the way the elements themselves seem to tell the same tale. People, through generations of curiosity and science, learned that stars were like time machines, capable of revealing the secrets of the past. When astronomers look at the composition of stars and distant galaxies, they find a specific mix of hydrogen, helium, and traces of other elements. The ratios are just right, matching what you'd expect if the universe began in a hot, dense state and then rapidly expanded, cooling as time passed. It's like looking at an ancient recipe left behind by a long-gone chef, with just enough salt and spice to tell you exactly what went into the dish. These pieces of evidence are like pages in an ancient, cosmic diary. They all point back to a time when everything we see, touch, and know was compressed into an unimaginably small space. From there, it all began to expand, to unfold, creating the vast tapestry of galaxies, stars, and planets that we see today. Scientists, just like the rest of us, are drawn to these mysteries not just out of a quest for knowledge, but because they touch something deeply human, the desire to understand where we come from and what place we have in this universe that seems both impossibly vast and intimately connected to our existence. Imagine sitting by the ocean, watching the waves roll out towards the horizon. As they move further away, you notice the sound fading, becoming quieter with distance. Now imagine that instead of water, it's light stretching out in waves through the universe. That's what happens when we look at the light from distant galaxies. The light isn't just fading, it's stretching out, shifting towards the red end of the spectrum. This phenomenon, known as redshift, is a lot like those waves, telling us that those galaxies are moving away from us. When scientists first observed this, it wasn't just a quirky discovery. It was like reading a secret message hidden in the fabric of space itself. The further a galaxy is, the more its light shifts to red. It's not that these galaxies are changing color like leaves in autumn, but rather, space itself is expanding, like a balloon slowly inflating. As this cosmic balloon expands, it carries everything with it, stretching the light waves from distant stars and galaxies along the way. It's as if each of these galaxies is a tiny boat, floating on the surface of a pond that's steadily growing wider, drifting further apart as the water stretches. For humans, it's not just a matter of seeing a change in color. It's realizing that we live in a dynamic universe, one that is still in motion after billions of years. The redshift is like a time capsule, a direct way of seeing that space is growing, not shrinking or staying the same. The expanding universe wasn't something we could see with the naked eye, but rather something we had to learn to listen for, like hearing that distant echo in the waves. The real wonder comes when you imagine yourself as an astronomer in the 1920s, peering through a telescope and realizing for the first time that this redshift meant the universe had a beginning. The galaxies aren't just drifting like clouds. They're part of a grand, unfolding story where time and space themselves are stretching out. Each redshift measurement is like a step backward in time, a hint at a universe that, long ago, was smaller, hotter, denser, and filled with potential. It's a profound reminder that even the stars, distant and ancient as they are, carry the history of the cosmos written in the light they send our way. Think about a cook in a kitchen, carefully following a recipe for a special dish, but imagine that this recipe is for the universe itself. The ingredients aren't flour or sugar, but the simplest elements: hydrogen, helium, and a sprinkle of lithium. These elements were cooked up in the first minutes after the Big Bang, during a time known as Big Bang nucleosynthesis, when the universe was unimaginably hot and dense. As it rapidly expanded and cooled, it was like turning down the heat under a boiling pot, allowing just the right conditions for these elements to form in precise amounts. Now, fast forward billions of years to scientists peering through telescopes, studying distant stars and galaxies. They look at the light coming from these celestial bodies, breaking it down like a prism, splitting sunlight into a rainbow. What they find hidden in that light is a fingerprint, a very particular blend of hydrogen and helium, with just a trace of lithium. It's not random. It matches exactly what you'd expect if the universe started with a Big Bang. It's as if the universe left behind an ancient recipe card, and these primordial elements are the ingredients it was able to mix together before things cooled down too much. This fingerprint of elements is everywhere. When we observe old stars or remote gas clouds that haven't yet been cooked into new stars, they show that same blend. There's too much helium, for example, to have been created solely in the furnaces of stars later on. Stars are like cosmic forges that can produce more complex elements, but they start with the universe's original stockpile. The amounts of hydrogen, helium, and lithium we see today are too perfect to be explained any other way. They're like clues from the universe's birth, left in plain sight for us to find. For humans, this realization is like stumbling upon an ancient family heirloom, one that tells you something fundamental about your own origins. It's humbling to think that the hydrogen in the water we drink and the helium in party balloons has a connection to the first seconds of the cosmos. These elements are the threads woven through time, carrying a memory of the universe's earliest moments. It's a story that wasn't told through words, but through the quiet, enduring presence of atoms that formed when the cosmos was just beginning to unfurl its mysteries. Imagine watching a single star explode in a galaxy millions of light years away, its final act sending out a flash of light that cuts through the darkness of space. This is a supernova, a star's dramatic end, but for astronomers, it's also a cosmic beacon. These stellar explosions, particularly a type called Type I supernovae, have become crucial for measuring the universe's expansion. What makes them so special is their predictability. When a white dwarf star in a binary system pulls in just enough matter from its companion, it reaches a tipping point and explodes in a very specific, bright way. It's like a cosmic firework that goes off with a predictable burst of brightness. Because these supernovae shine with nearly the same intrinsic brightness, they act like universal mile markers. Imagine driving down a highway at night with streetlights of known brightness stretching into the distance. The further away the streetlight, the dimmer it appears. By measuring how dim these supernovae look from Earth, scientists can determine how far away they are. But there's more to it. As they observe these distant supernovae, they also notice how the light is stretched out, shifted towards the red end of the spectrum, telling them how fast the galaxies hosting these supernovae are moving away. This relationship between distance and speed is key to understanding the universe's expansion. In the late 1990s, two teams of astronomers used these supernovae to make a surprising discovery. Not only is the universe expanding, but it's doing so faster than expected, accelerating as if something mysterious, what we now call dark energy, we're pushing everything apart. It's like being on a roller coaster and realizing, halfway through, that the ride is speeding up when you thought it would slow down. For scientists, seeing this through the eyes of supernovae is a reminder that the universe is not just a static, distant place, but a dynamic, evolving landscape. These exploding stars have become like lighthouses scattered across the cosmos, each one revealing a little more about the path we're on, helping us map out the vast, accelerating ocean of space we live in. The data from supernovae aren't just numbers. They're glimpses into the history and future of everything around us, revealing a universe that's more restless and mysterious than we ever imagined. Picture the universe not as a silent void, but as a vast, vibrating drumhead. Gravitational waves are the ripples that travel across this drum, carrying with them the echoes of cataclysmic events, black holes colliding, neutron stars merging, and perhaps even the faint murmurs of the universe's birth. When the first gravitational waves were detected in 2015 by the LIGO Observatory, it was like opening a new sense, one that allowed us to feel the vibrations of space-time itself. These waves aren't like light or radio signals. They move through space itself, squeezing and stretching it ever so slightly as they pass. This new way of listening to the universe has offered a fresh perspective, especially when it comes to the earliest moments after the Big Bang. Gravitational waves provide a kind of insight that light cannot. The light we see today, the cosmic microwave background, comes from about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. But gravitational waves, theoretically, could carry information from even earlier, moments after the Big Bang when space was still a seething, chaotic foam. If we could detect these primordial gravitational waves, it would be like hearing the universe's heartbeat from its infancy, offering a direct glimpse into the extreme conditions of those first moments. Even though we haven't yet detected these primordial waves directly, the discovery of gravitational waves has proven that this sort of cosmic messaging is possible. It has fueled our imagination and our science, driving researchers to build even more sensitive detectors, ones that might one day catch those earliest ripples. It's a bit like discovering an ancient language, one that, with time and study, might reveal hidden chapters of our universe's story. And while most of the waves we've heard so far come from collisions billions of years later, the possibility that we might one day hear the faint, original echoes of the Big Bang has fundamentally changed how we think about the universe. It's a shift in perspective. Gravitational waves have turned space-time from a static backdrop into something dynamic, alive, and capable of preserving traces of events that shaped everything. It's as if we've found a new way to listen to the cosmos breathing, and that breath carries hints of the universe's first moments, its wild beginnings, and the forces that have shaped its vast, ever-expanding story. The Big Bang Theory suggests that the universe began from a single, unimaginably dense point, an instant of pure energy that expanded rapidly to create everything we know today. At first glance, this origin story can feel unsettling to people searching for deeper meaning. If the universe started as a random explosion of matter and energy, where does that leave us? There was no guiding hand, no grand design, just the raw unfolding of physical laws. The universe didn't intend for stars to form, or for galaxies to spiral into their graceful dance. It certainly didn't plan for Earth to come into being, or for human beings to evolve from scattered stardust billions of years down the line. This randomness can evoke a sense of cosmic indifference, a feeling that we are accidental passengers in a universe far too large and ancient to care about individual lives. And yet, that very same indifference can provoke something strangely beautiful in us. The absence of an inherent, predefined purpose doesn't have to translate to purposelessness. If the universe didn't dictate meaning, then it means meaning is something we create ourselves. This responsibility is daunting, but also liberating. There's no cosmic checklist to fulfill, no script we're expected to follow. In a sense, we are free to write our own story, to give weight to what matters most to us. A shared laugh with a friend, the warmth of sunlight on our skin, the drive to seek knowledge. These become more meaningful precisely because they emerge from our choices, not from some celestial decree. The Big Bang also implies something deeply existential, that everything we know is connected. Every atom in our bodies was once part of a star, forged in the nuclear heart of distant suns before being scattered across space to eventually find its way here. This doesn't give us cosmic importance, but it does suggest continuity. The elements that make us who we are, carbon, oxygen, iron, will one day return to the cosmos to be reused in ways we can't imagine. There's something humbling and oddly comforting in that. Our lives, no matter how fleeting, are part of a much larger cycle of transformation and renewal. Human beings, in our search for purpose, often long for certainty. The Big Bang offers no such certainty, only a story of constant change. And this idea that the universe is always in motion, expanding, evolving, can be unsettling. We like to think of meaning as something solid, something we can cling to. But perhaps meaning, like the universe itself, is something dynamic, something we create and recreate as we move through life. The Big Bang reminds us that the universe started with the barest possibility, and from that possibility came everything. Likewise, our lives are filled with countless possibilities, most of which are fleeting, but some of which can shape who we become. Maybe the real beauty lies in that very impermanence. Nothing we build will last forever. Not our relationships, our ideas, or even our species. But the fact that we can create these things at all, in a universe that owes us nothing, is remarkable. The Big Bang doesn't give us a clear answer about what life means, but it suggests that the raw ingredients for meaning are everywhere, scattered through our experiences and connections. It's up to us to find them and make them matter. The Big Bang suggests that the universe, as we understand it, had a beginning, a specific moment when time, space, energy, and matter emerged from a state of unimaginable density and heat. Before that, there was no before in any sense that makes intuitive sense to us. Time itself seems to have started with that singular event, and this idea feels deeply unsettling. As humans, we're used to thinking in terms of causes and sequences. Every effect has a cause, every beginning suggests something that came before. But the Big Bang challenges that instinct. If there was no space and time prior to this moment, how do we make sense of the universe having a beginning at all? It forces us to confront the limits of our understanding and teases at a mystery that may never yield to logic. This idea has existential weight because we are creatures wired to search for reasons, whether it's why a person enters our life or why the universe exists at all. The notion that the universe might have come from nothing or from conditions we cannot even grasp brushes up against those deep human urges. It makes us wonder, if the universe began, did something set it into motion? Was it pure chance, or was there intention behind it? And if the latter, what does that intention mean for us? This is where theological questions naturally arise. Some see in the Big Bang echoes of creation stories, believing it hints at a divine spark or a creator who set everything into motion. Others resist that interpretation, seeing the birth of the universe not as evidence of a higher power, but as the beginning of a cold and indifferent process. Theologically, the Big Bang leaves space for both belief and doubt. For some, it reinforces a sense of divine mystery, a God so vast that even the science behind creation hints at something incomprehensible. For others, it's proof that we don't need supernatural explanations. The universe could be self-contained, its origin rooted in laws of physics that we are only beginning to grasp. Neither view can fully answer the fundamental question of why there is something rather than nothing, and that tension between what we know and what lies beyond our grasp creates an existential restlessness. On a human level, the idea of a beginning makes us think about the flow of time in new ways. If the universe began, does that mean it will also end? Does it make our lives, which already feel brief, even more fragile and insignificant? Or does knowing that the universe has a timeline, no matter how vast, give our existence a strange sense of kinship with it? Just as the cosmos had a first moment, we have first moments. The first breath we take, the first time we fall in love, the first time we lose someone. In both cases, beginnings are laced with uncertainty, but they carry potential too. Every beginning implies the possibility of something unfolding, growing, changing. And yet, there's a paradox here. While the universe might have had a beginning, it seems it wasn't a beginning in the way we usually think, like the start of a story with a neat progression. The universe has no final destination, no particular point it's trying to reach. It's just expanding endlessly and relentlessly, without a goal. That realization forces us to rethink how we find meaning. We often look for narratives to give shape to life, believing things need a purpose to be worthwhile. But the Big Bang suggests that life, like the universe, may not come with any built-in meaning. If the cosmos doesn't need a purpose to exist, maybe our lives don't need one either. Maybe it's enough that they simply are. What's strange and beautiful about this realization is that it doesn't necessarily lead to despair. If the universe began without meaning, that leaves room for us to create meaning as we go. It's like being handed a blank page, not because someone expects us to write anything, but because there's nothing stopping us from doing so. In the end, the idea that the universe had a beginning makes us feel both small and significant. We are tiny sparks in an ancient cosmos, fleeting and fragile, but also part of the same vast story, one that began in fire and light and continues through every thought, every connection, every experience we create along the way. The idea that the universe might be fine-tuned, for life touches on a deep tension between wonder and randomness. On the one hand, the fundamental forces that govern the cosmos, gravity, electromagnetism, the strong and weak nuclear forces, are so precisely balanced that if even one of them were slightly different, life as we know it would be impossible. If the strength of gravity were minutely stronger or weaker, stars wouldn't form or collapse in the right way to create the heavy elements necessary for planets and life. If the ratio between the proton and electron mass varied even slightly, atoms might not hold together properly. Everything, down to the smallest particle, seems perfectly arranged for us to exist. It's hard not to look at that and feel like something intentional is at work, as if the universe were carefully adjusted so that one day we could open our eyes and look back at it, trying to understand where we fit in. But then, there's the other side. Maybe life is just an accident, a rare blip in an indifferent, chaotic universe. After all, the cosmos is unimaginably vast, with billions of galaxies, each containing billions of stars. Life appearing on Earth could just be the result of probabilities playing out over an enormous canvas of possibilities. The universe may not be fine-tuned at all. It might just be that we happen to live in one small corner where the conditions were right, and it only feels special because we're the ones lucky enough to experience it. It's like hitting a jackpot after rolling the dice an unimaginable number of times. From this perspective, life isn't inevitable or planned. It's a rare fluke, something that could have easily never happened at all. The thought that our existence might be a cosmic accident stirs conflicting emotions. On one level, it can feel profoundly isolating. If we are the result of random chance, the universe doesn't care whether we exist or not, and there's no grand purpose waiting to be uncovered. For some, that feels like a void, a realization that nothing is guaranteed, that the cosmos could go on perfectly well without us, and someday it will. But there's also a strange kind of awe in that randomness. If life is as rare as it seems, if everything had to line up just right for us to be here, then every moment we experience becomes almost incomprehensibly precious. The odds against us were so staggeringly high. Yet here we are, thinking, breathing, wondering about it all. Even if the universe didn't mean for us to exist, the fact that we do feels almost like a miracle, not because someone planned it, but because it could so easily have never happened at all. When we think about fine-tuning, it's easy to fall into the trap of seeing life as the goal, as if the universe is special only because we're here to observe it. But maybe life is just one expression of the universe's complexity, like the formation of stars or the dance of galaxies. We're not the inevitable conclusion of the cosmos. We're part of its unfolding story, no more or less meaningful than any other outcome. If conditions had been different, maybe something else, something equally remarkable, would have emerged instead of us. That thought can be both humbling and uplifting. The universe isn't tailored to us, but it still gave rise to us. That's not nothing. This tension between fine-tuning and chance invites us to think deeply about what it means to matter. Does something need to be planned to be meaningful? Does randomness make life any less significant? For humans, it's natural to crave purpose, to want to believe that our existence was written into the fabric of the universe. But maybe the real beauty lies in the uncertainty. The universe didn't promise us anything, not a place to live, not even existence itself. And yet, through billions of years of chance and unfolding physics, here we are. Whether the universe is fine-tuned or not, life is rare and fleeting. Maybe it doesn't matter whether we were intended or accidental. What matters is that, for this brief window of time, we get to experience the universe in all its vastness and mystery. The idea that the universe had a beginning forces us to rethink what time, existence, and reality actually mean. We usually treat time as something constant and endless, a river flowing in one direction, carrying everything with it. But if time itself began with the universe, that means it's not some infinite backdrop. It's something that emerged, something that could have not existed at all. This is unsettling because we rely on the idea of time to structure every part of our lives. If time has a starting point, it feels like there should be an explanation for what came before, yet there was no before in any meaningful sense. This realization pushes us out of the familiar, linear way we experience existence and into a strange space where even our basic intuitions start to break down. It's hard not to feel small in the face of a beginning. Everything we know, every memory, every moment we experience, takes place within a framework that's been ticking ever since that first cosmic instant. And just as our lives begin and end, the universe seems to carry the same condition. It had a starting point and might have an end. This puts everything into a sharper perspective. If the universe itself is finite, then existence isn't some eternal constant. It's more like a window, brief and limited. That idea can weigh on us. It raises questions about how much anything matters if time will one day move on without us and, ultimately, without everything. We already struggle with the passing of time in our personal lives, relationships fading, moments slipping away. And now we're faced with the reality that even time itself isn't something permanent. It all had to begin somewhere, and that means it could just as easily stop. This concept also changes how we think about what's real. We tend to assume that reality is built on stable foundations, but the idea that the universe had a beginning suggests that even those foundations might be contingent. Space, time, matter. Everything we experience as real is part of a process that had a starting point. If reality itself is something that unfolded over time, it raises the question, is anything truly stable? What we think of as the fabric of existence might just be a fleeting state, a temporary arrangement that happened to emerge from a singular beginning. It makes you wonder whether other kinds of existence, other forms of reality, might be possible beyond what we can imagine. If time and space began once, why assume that they're the only way reality can exist? There's a strange intimacy between our personal experience of time and the universe's story. Just as we move from one moment to the next, never able to go back or hold on to anything for long, the universe has been expanding, cooling, and evolving ever since that first instant. Our lives mirror that cosmic movement. We are born, we grow, we change, and eventually, we end. The difference is that we often think of the universe as eternal, something solid and dependable even as our individual moments slip away. But the realization that the universe had a beginning reveals that we're not just temporary beings living in an endless world. Everything around us is part of the same fragile flow of time. There's something both humbling and liberating about this. If the universe began, then the conditions we live in, time, space, existence itself, are not fixed laws of some eternal reality. They're part of a larger process that we're swept up in. It means that change isn't just something that happens within our lives. It's woven into the very nature of the universe. And that means there's room for us to find meaning not in permanence, but in movement. Reality isn't something we grasp and hold. It's something we experience as it unfolds, moment by moment. Just as the universe began, everything we do is part of some beginning, some unfolding process that will continue beyond us. And maybe, in the end, it's not the permanence of things that matters, but the fact that they happen at all. Technology has always been a lens through which humanity seeks to understand the universe, and few inventions have transformed our view of the cosmos more profoundly than tools like the Hubble Space Telescope and particle accelerators. Each represents a step in our quest to unravel the origins of existence, helping us peer further back in time and deeper into the fabric of reality than our ancestors could ever imagine. The Big Bang, the idea that the universe began as an unimaginably hot and dense singularity, expanding over billions of years, is not just an abstract theory. It's the closest thing we have to a cosmic birth story. But this story only began to take shape because human curiosity compelled us to build machines capable of seeing the invisible. When Hubble was launched into space, it was more than a telescope. It was a gift to generations of astronomers whose dreams had been limited by Earth's atmosphere. Before Hubble, the view from ground-based observatories was blurred by air currents and light pollution. But in the vacuum of space, with its precision optics, Hubble captured breathtaking images of galaxies billions of light-years away, revealing how these structures evolved over time. It didn't just offer us pretty pictures, it showed us the aftermath of the Big Bang. Each distant galaxy observed is like a time capsule, light traveling across eons to reach us, hinting at the early conditions of the universe. By studying this light, scientists confirmed the accelerating expansion of the universe, a discovery that later earned a Nobel Prize. This raised new questions. If the universe is accelerating, what unseen force, what dark energy, drives this expansion? Hubble, in its quiet way, pushed us toward these profound puzzles. On a much smaller, yet equally staggering scale, particle accelerators have been our windows into the first few moments after the Big Bang. Facilities like CERN's Large Hadron Collider, LHC, allow us to recreate, in controlled bursts, the conditions that existed microseconds after the universe began. When particles are smashed together at nearly the speed of light, they reveal traces of fundamental forces and particles that stitched the early cosmos together. The 2012 discovery of the Higgs boson, sometimes called the God particle, though scientists prefer less dramatic terms, was a landmark moment. It confirmed a piece of the standard model of physics, helping explain how particles acquire mass. Yet, it also reminded us how much remains unknown. Why does the universe contain matter at all? Why did it not collapse into nothingness? Beyond the data and formulas, there's a deeply human story running through these discoveries. It's the story of people, scientists, engineers, dreamers, who build instruments to answer questions that most of us can only vaguely comprehend. They spend lifetimes designing detectors, calibrating mirrors, and analyzing beams of particles, all for the chance to glimpse the universe's earliest moments. Their work is relentless, often frustrating, and yet thrilling. Every time they send a telescope into space or fire up a particle collider, it's a reminder that understanding the cosmos requires not just knowledge, but imagination. These technological advances have also shifted how we see ourselves. Knowing that every atom in our bodies was forged in ancient stars, or that we live in a universe still stretching outward from a primordial explosion humbles us. It reminds us of our place in the grand tapestry of time. But the deeper we go into these mysteries, the more questions we find waiting. What came before the Big Bang? Are there parallel universes, or will this one collapse upon itself? Ultimately, our tools, like Hubble and the LHC, have shown us that the universe is far stranger and more beautiful than we ever suspected. They have pulled us closer to the edge of the unknown, not to provide final answers, but to keep us moving forward, driven by the hope that with every discovery, we take another small step toward understanding where we came from, and maybe even where we are going. The next big breakthroughs in our understanding of the universe's origins may come from ideas and technologies that feel like whispers from the future, things we can barely imagine today but are slowly becoming reality. New discoveries that could reshape our view of where everything began won't just come from refining what we already know. They might challenge the very foundation of our understanding. What if the Big Bang wasn't the beginning but just one chapter in an eternal cycle of expansion and collapse? Or what if space and time themselves are only part of a larger, hidden structure we haven't yet glimpsed? One possibility lies in the detection of primordial gravitational waves, ripples in space-time left behind from the first fractions of a second after the universe came into being. These waves would carry with them the imprint of the universe's birth, revealing what happened in that mysterious moment called inflation, when everything expanded faster than the speed of light. If instruments like the European Space Agency's LISA mission or upgraded ground-based detectors catch these whispers from the earliest moments, it would confirm inflation theory in ways we've never managed before. But what's exciting is the potential for surprises. The patterns in those waves could hint at something far stranger, a multiverse, perhaps, where other universes bubbled into existence alongside our own. Just imagining this possibility reshapes the question from, how did our universe begin? To why does this one universe, out of countless possibilities, look the way it does? Another revolutionary step may come from uncovering the nature of dark matter and dark energy, those two invisible forces that make up most of the universe but still defy direct observation. New space telescopes like the James Webb and the upcoming Nancy Grace Roman telescope are already helping us hunt for clues, but it could be a discovery as unexpected as the Higgs boson that cracks the mystery open. Maybe the key will come from experiments deep underground, in places where sensitive detectors wait for the faintest sign of a dark matter particle. Or it might involve an entirely new physics, something beyond our current understanding of space, time, and matter, that forces us to rethink the Big Bang as just one piece of a larger puzzle. Quantum physics, too, could have something astonishing in store for us. Right now, we understand the universe at two extremes. Relativity describes the cosmos at large scales, while quantum mechanics governs the microscopic world. But when we try to bring those two worlds together, everything falls apart. Our equations stop making sense. Many physicists believe that unlocking the true origins of the universe will require a theory of everything that bridges these two realms. Ideas like quantum gravity or string theory might hold the answers, though they remain largely untested. If future experiments or new mathematics reveal how quantum fields and gravity dance together at the birth of the universe, it would rewrite physics as we know it. And then there's the possibility of discovering something we haven't even dreamed of, some signal or phenomenon that doesn't fit any of our theories, forcing us to start from scratch. In science, the biggest leaps often come not from finding what we expect, but from finding what we didn't even know to look for. Imagine if an alien intelligence sends us knowledge encoded in a pattern of radio waves, revealing insights into the universe we couldn't discover on our own. Or what if we uncover evidence that space and time are emergent properties, not fundamental realities? Such a discovery would make the Big Bang just a small detail in a much grander, deeper framework of existence. What makes all of this so thrilling is the sheer unpredictability of it. Humanity has always lived on the edge of what is known and unknown, and every generation of scientists brings us closer to a new horizon. But with every new answer, the cosmos also gives us more questions. Maybe the true revolution won't come from finding a neat, final answer about the origins of the universe, but from learning to live with the mystery, reveling in the fact that the more we understand, the more extraordinary and unknowable everything seems. The James Webb Space Telescope, now orbiting far beyond the distractions of Earth, is not just another telescope. It feels like humanity stretching its fingers into the deepest corners of time, reaching out to touch the first sparks of creation. What sets Webb apart is its ability to see the universe in infrared light, a part of the spectrum invisible to the human eye. As light from ancient galaxies travels billions of years through the expanding universe, it stretches into longer, redder wavelengths. Webb was built to catch this faint, ancient glow, light that left its source more than 13 billion years ago, perhaps only a few 100 million years after the Big Bang. With its vast, golden mirrors and precisely calibrated instruments, Webb offers a glimpse into the period known as the Cosmic Dawn. This is when the first stars and galaxies ignited, ending the dark ages of the universe and flooding space with light. We know almost nothing about these earliest objects. How did the first stars form from clouds of hydrogen and helium? Were these stars enormous, short-lived beacons that exploded into supernovae, seeding the cosmos with heavier elements? Or were they quieter, more gradual builders of galaxies? Every time Webb focuses on a distant cluster of light, it inches closer to answering these questions. But what makes this process remarkable isn't just the data. It's the thrill of discovery. Every time Webb sends back an image, thousands of scientists around the world hold their breath, knowing that hidden in those glowing dots might be something unexpected. A glimpse of a galaxy too old or too strange to fit our models. Even more exciting is Webb's ability to peer into the dense clouds of gas and dust that surround newborn stars. With ordinary telescopes, these regions are like veiled secrets, blurred or completely invisible. But Webb's infrared vision cuts through the dust, revealing the delicate process of star formation and the birth of planetary systems. What we learn here isn't just about distant galaxies. It might also tell us how our own solar system came to be. If Webb can spot the chemistry of forming planets or detect signs of water and organic molecules in the atmospheres of distant worlds, it could hint at how life itself might emerge in the universe. And then there's the chance Webb might stumble upon something completely unanticipated. When Hubble launched decades ago, no one expected it to reveal the accelerating expansion of the universe or uncover entire fields of galaxies packed into tiny, seemingly empty patches of sky. Webb's mission carries that same potential for the unexpected. Maybe it will capture the birth of a black hole, or detect patterns in early galaxies that challenge our understanding of cosmic evolution. Or perhaps it will find evidence that dark matter, that strange invisible substance shaping the universe, behaves in ways we've never imagined. These missions aren't just technical achievements. They are the result of decades of human effort, perseverance, and vision. Thousands of engineers, scientists, and dreamers came together to make Webb a reality, often working through setbacks and uncertainties. For years, it seemed like the telescope might never launch. Technical delays, budget overruns, and even fears of failure hung over the project like storm clouds. And yet, they pressed on. They pressed on because the urge to know, really know, what happened at the beginning of time is something that drives us all. When Webb looks into the distant past, it's not just a machine gazing into the cold emptiness of space. It's us, fragile, curious beings on a small planet, trying to understand where we come from and what role we play in this vast, unfolding story. The discoveries Webb makes in the coming years will almost certainly change the way we see the universe and ourselves. But the beauty of these missions is that they always leave us with more questions. Even as we learn about the first stars and galaxies, we'll wonder what came before them. Even if we find planets with the ingredients for life, we'll ask if they ever harbored anything like us. That's the human spirit, really, never content with what we know, always searching for the next mystery to unravel. And the best part? Webb is just the beginning. With every new discovery it makes, we'll dream of even more powerful telescopes, even deeper journeys into the unknown. The search for answers about the early universe goes beyond telescopes. It dives deep into the world of particles, the tiny building blocks that existed at the very beginning. Advances in particle physics, like uncovering the secrets of the Higgs boson, bring us closer to understanding the fundamental forces that shaped everything from the earliest moments of time. The Higgs is more than just another particle. It's the key to understanding how matter as we know it even exists. Without it, particles wouldn't have mass, and the universe would have remained a chaotic blur of energy, never forming stars, planets, or life. But there's more to this story than just physics. It's about human beings trying to crack open nature's deepest mysteries, following threads of discovery that could change the way we understand reality itself. The Higgs boson, discovered in 2012 at CERN's Large Hadron Collider, confirmed a theory that had been half a century in the making. Its discovery was like finding a missing piece in a puzzle scientists had been assembling for decades. But far from closing the book, the Higgs has opened new doors into unknown territory. One of the biggest questions is why the Higgs field, the invisible field that gives particles mass, exists at just the right strength to allow the universe to form the way it did. If it were even slightly different, atoms would never have come together, and we wouldn't be here to ask these questions. This delicate balance makes physicists wonder if something deeper is at work. Maybe our universe is just one version in a sea of possible realities, and only the ones with the right conditions can create matter. The Higgs boson hints at these tantalizing possibilities, but it also reminds us of how much we still don't know. Advances in particle physics could go even further in explaining what happened during the earliest moments after the Big Bang. In those first fractions of a second, the universe was unimaginably hot and dense, a place where particles and forces behaved in ways we've never witnessed since. Understanding how forces like gravity, electromagnetism, and the strong nuclear force emerged from this primordial state is one of the great unsolved mysteries of physics. Right now, our theories can't quite connect the dots between these forces at the quantum level. Something crucial is missing. The discovery of the Higgs boson was a step toward that deeper understanding, but it's clear we need more pieces to complete the picture. Future experiments might reveal new particles or forces that existed only during those first moments of creation, giving us a glimpse into the processes that shaped the universe's earliest structure. There's also the chance that particle physics could uncover the nature of dark matter, that mysterious substance that makes up most of the matter in the universe but refuses to interact with light. Some theories suggest that dark matter particles could be connected to the Higgs field or involve forces that were only active during the birth of the universe. If experiments at CERN or other colliders detect traces of dark matter, it would be like opening a hidden chapter in the universe's origin story. It would tell us not just what the universe is made of, but how it evolved from a uniform burst of energy into a rich tapestry of galaxies, stars, and life. What makes all this so compelling isn't just the discoveries themselves. It's the way these experiments reflect human ambition and creativity. Building a particle accelerator capable of recreating the conditions of the early universe takes decades of planning, thousands of people working across borders, and an unshakable belief that the answers are worth the effort. Physicists spend their lives sifting through mountains of data, hoping to find one faint signal that might unlock a new understanding of the universe's beginnings. It's a kind of modern-day alchemy, turning collisions of particles into insights about the deepest forces of existence. The quest to understand the Higgs and the forces that shaped the early universe is about more than science. It's about a shared human longing to make sense of our place in the cosmos. Every new discovery reminds us that the universe is both stranger and more beautiful than we ever imagined. But it also leaves us with more questions. Why does the Higgs field exist at all? What lies beyond the standard model of physics? Could there be other forces or dimensions waiting to be uncovered? Advances in particle physics won't give us all the answers right away, but with each experiment, we get a little closer to understanding the invisible forces that gave birth to everything we see around us. And perhaps in the process, we come a little closer to understanding ourselves. As we bring this cosmic journey to a close, it's truly mind-bending to think that everything, the stars, the galaxies, even the very atoms that make us up, emerged from a single, unfathomable event, the Big Bang. From the birth of time itself to the mysteries of dark matter and dark energy, we've only scratched the surface of the incredible story our universe has to tell. And who knows, as our technology evolves and our curiosity deepens, we may one day unlock even greater secrets about where we came from and where we're headed. But for now, I hope you've enjoyed this exploration as much as I have. The universe is vast, and there's always more to discover. If you'd like to continue the journey with us here at Quiet Universe, feel free to like the video and subscribe. It's a small click for you, but a giant leap for this channel. Thanks for watching, and until next time, keep wondering, keep asking, and keep looking up at the stars.